Now, as always, don't forget that I sell my perfect answer revision guides on my website, which is www.sciencewithhazel.co.uk. If you click on this card, you'll be able to go and purchase yourself a copy. It is available now in all 3 sciences. So if you enjoy my videos and you enjoy the way in which I describe and explain things, that is where you will find a distillation of my videos. You'll also find information about revision courses if you're keen on attending, school licenses and private tuition. However, enough about that, let's get started. So we're going to start by looking at solids, liquids and gases. So when we look at solids, liquids and gases, be prepared to draw their particle diagrams. Notice that solids have particles which are in very fixed arrangements, and that's because the particles vibrate around in fixed positions, they have little kinetic energy and there are strong forces between them. Moving to liquids, you see that the particles are slightly more widely spaced apart. They're not touching quite as much, so they have intermediate forces between them and they vibrate more and they don't have fixed positions. Gases now, so you need your particles to be further apart. This is because they have large amounts of kinetic energy. Obviously they're not held in fixed position and there are weak forces between the particles, and here's your summary now. Let's start naming the correct conversions between all these various states of matter. So remember, if you're going from a solid to a liquid, that is melting, like a solid ice block turns into water, melting. If you go the other way and the water turns into ice, clearly that will be freezing. If you have a liquid and it turns into a gas, that will be boiling or evaporating. And then when you have a gas and it turns back into a liquid, that is condensation. So that's what happens when you have a shower and you see it getting all misted up on the windows. Condensation is occurring here. Touching slightly more on evaporation, so how does the evaporation of a puddle or any liquid happen really? So what you find is that the particles have differing kinetic energy. Now those particles with the most amount of energy will evaporate first and they will leave the surface of the liquid. And what will happen is it will mean that the remaining particles have lower average kinetic energy. Do notice that in a closed container, condensation and evaporation will be occurring simultaneously, which means at the same time. The specification now touches on diffusion, which you should be aware from biology. So diffusion is the net movement of particles from an area of high concentration to an area of low concentration. And because that's down the concentration gradient, you find that no energy is required. It is a passive process. So that means in any scenario where you have large amounts of particles in one place, they will drift and move across to somewhere, some region which has a lower density or concentration of these particles. And the example we like to look at in chemistry is, you might have seen your teacher go through it in class. You've got this huge glass tube, and one end you have ammonia, the other end you have hydrochloric acid, and effectively their concentrations are high either end of the tube, and obviously the particles start to diffuse. So the ammonia starts to move towards the hydrochloric acid, and where they meet, a chemical reaction takes place and ammonium chloride is produced, which we see as a white ring. Now, the location at which this white ring occurs will tell you something about how quickly diffusion is happening, because clearly if the white ring occurs in the middle of the tube, it means that the ammonia and the hydrochloric acid diffused equally quickly across. However, this isn't true. What actually happens is that the ring forms much closer to the hydrochloric end, and that means that the ammonia has diffused further and faster. And what is the reason for this? It's simply because it has a lower relative atomic mass. Let's do a list of apparatus and be familiar with recognising them and potentially drawing them. So first of all, our Bunsen burner. The easiest way to draw that is with an arrow going upwards with the word heat underneath. With chemistry, it's not an art competition. It's not about how well you can draw stuff. You need to draw it in a very scientific way. So the tripod, remember that's what you heat stuff on, will look like this. And on top of the tripod often sits a gauze, which lots of people pronounce that quite strangely. That's how you say it and that's how you spell it. And then that often sits on top of a heat-proof mat. And then while I'm at it, I might as well put an evaporating basin on the top so I don't have to draw it later. Your beaker is very basic, hopefully less wobbly than that. You have a conical flask, which is more triangular at the bottom. If you're carrying out a filtration technique, remember that's separating an insoluble solute from a solvent, you're going to use a filter funnel, which tends to sit atop a beaker, and you need filter paper in there. Measuring cylinders, remember they're used to measure out inaccurate volumes of liquids. Something like this is more than adequate. Scales are used to measure the mass or weight of objects. You might use a thermometer if you're needing to find out the temperature. And a stopwatch is good when you're looking to measure rates of reaction, for example, so the time it takes to evolve 100 centimetres cubed of gas, for example. That's going to look very similar to your scales. Do notice, although I've already pointed out the measuring cylinder is a very inaccurate way of measuring volume, you've got far more accurate ways using pipettes, so like a glass pipette that you use in titrations. That will accurately measure out 25 centimetres cubed of liquid, for example. And then you have the very long, skinny burette. I really don't think you'll be asked to draw this. Remember, that has a little tap, and that measures out extremely precisely. Looking at solutions now, so be aware of the solution words you need to know and their definitions. So we're going to use coffee being dissolved in hot water as our example so that you can actually understand the words I'm saying. So we're trying to make a nice cup of coffee, and we're going to start by looking at what a solute is. So a solute is a solid which dissolves in a solvent. So in the case of our coffee example, the solute is the coffee grounds. The solvent is the liquid in which the solute dissolves. So in our example, that would be the hot water. The solution is the mixture of the solvent and solute. So that would be the nice cup of coffee that we make. And then a saturated solution is one where you can't dissolve any more solute into the solvent. So it's at its maximum capacity effectively. We now need to touch on separation techniques. So I'm going to give you all the different examples and how you would use each of them. So first of all, filtration. You are going to use this to separate an insoluble solute from a solvent. And your example here could be sand and water. The reason filtration works so well is you pour the mixture through the filter funnel containing filter paper, and what you'll find is the sand stays in the funnel, the water flows through into the beaker below. So you've separated your insoluble solute from the solvent. And be prepared to label all the apparatus involved and be able to draw simple diagrams. Getting slightly more complicated now, we now have a soluble solute that needs separating from a solvent. This could be something like salt being separated from water. So clearly filtration won't work because the salt will go straight through into the beaker below, which is why we need to use evaporation. So you have a tripod with gauze on the top, an evaporating basin containing the salt solution. You boil using a Bunsen burner. The excess water boils off and you're left behind with salt in the evaporating basin. Next up, we're separating immiscible liquids. So these are liquids which do not mix. A good example here is oil and water. And you will find that oil, and you can see this at petrol stations, if for some reason it's rained and then petrol's ended up in the puddle, you can see the petrol floating on top of the water, and that's what happens with oil too. So in this case, you can just put it into a funnel, you can open a tap and the water will drain out first, close the tap and you'll leave the oil behind in the funnel. Now liquids of different boiling points, for example ethanol and water. Clearly evaporation and filtration won't work here, and this is where you use simple distillation, and simple distillation relies on the fact that liquids have different boiling points, because what happens is you use a Bunsen burner to boil the mixture of liquids, and the liquid with the lower boiling point will evaporate first. So that would be the ethanol with a boiling point of 78 degrees Celsius, leaving behind the water below. And if you have a real mixture of liquids with lots of different boiling points, such as crude oil, this is where you'll use fractional distillation, which actually allows you to separate out many different liquids of different boiling points. Our last separation technique is chromatography. Remember, this is used to separate liquids of different solubilities, so that could be food colouring, dyes, inks, for example. Be prepared to describe how you set up a chromatogram. Remember, you have filter paper, which you draw a reference line on in pencil. You put the dots of ink along the pencil line, and then you dip the paper into water. As the water soaks up, it draws the dyes up the paper, and you can determine several things from that. So first of all, notice that you draw the reference line in pencil. Why? Because you don't want the pencil to spread and go flowing up the paper too, because that will disrupt your chromatogram. Notice that the ink which travels the furthest has the highest solubility, which kind of makes sense. And be prepared to use the formula, which is the RF formula. And that's the formula whereby the distance travelled by the component is divided by the distance travelled by the solvent. The final methods of purification you need to know about include heating with carbon and electrolysis. So let's start with heating with carbon. The most famous example of this is the blast furnace. And heating with carbon is used to purify metals, which are crucially less reactive than carbon. This genuinely only works because the carbon is more reactive and can effectively steal the oxygen from the impure metal. So in the case of the blast furnace, remember what you're adding here is iron oxide, and you heat with coke, which is your source of carbon. And then what you find here is that the iron oxide is reduced by that carbon, which has turned into carbon monoxide within the blast furnace, producing iron and carbon dioxide. Just make sure that that's balanced. Don't forget that they add limestone as a raw material, and that limestone is there to remove acidic impurities and ensure that that iron is as pure as possible. The acidic impurity we're talking about is actually silicon dioxide, which reacts with the calcium oxide from the limestone to produce calcium silicate, otherwise known as slag. If the metal we're trying to purify is more reactive than carbon, then clearly the blast furnace won't work because the carbon won't displace that oxygen, which is where we need to use the final purification method you need to know about, which is electrolysis, which, as the name suggests, is using electricity to purify the metal. And that's used in metals which are more reactive than carbon. It's a really frustrating process because it's incredibly expensive, and that's due to the high energy costs, simply because you need so much electricity. We're going to go into electrolysis in far more detail, but remember that the metal is reduced, which means it loses oxygen, gains electrons. If you're finding this hard, don't worry, we're going to go into this in way more detail when we talk about electrolysis properly, and that occurs at the cathode, which is the negative electrode. So, for example, aluminium is a very famous metal which is purified by electrolysis. So here it is undergoing reduction to produce pure aluminium. Looking at some fundamentals which underpin chemistry, we need to look at an atom, element, mixture and compound. So an atom is the smallest particle of a substance that can exist. There are probably more accurate definitions for this, and that will involve high level physics, but for all intents and purposes for your chemistry GCSE, this is what you need to know. An element contains only one type of atom, and it cannot be split by any chemical means. So basically, if you're given a list of substances and you're asked which is the element, cross-reference the list to the periodic table, and you'll soon be able to see if what you have is an element or not. If it's not in the periodic table, it is not an element. Compounds now, well, that's when you have two or more elements which are chemically combined, and what that means is you cannot separate them back into their constituent elements. And a good analogy for this is when you make a cake. So you add flour, eggs, sugar, and effectively when you bake it, it turns into a cake, and that's the equivalent of a compound because there's no way you can separate those cake particles back up into eggs, flour, sugar. That's not going to happen, and that's due to the chemical reaction that's taken place. A mixture is different to this. A mixture contains, as you would imagine, two or more elements, this time not chemically combined, so theoretically you should be able to separate your mixture into its constituent components. And now I'm just going to bring up an example table showing elements, compounds and mixtures, and you should have a go at potentially separating them out yourself and make sure you can tell the difference. When we look at a pure substance, this is a substance which contains only one type of material. So that could be, for example, one element, so carbon, or it could be one compound, such as carbon dioxide. But the point is there's nothing else in there contaminating it. If you think you have a pure substance and you want to look at its boiling point, be aware that a pure substance will have a fixed boiling point and should not boil over a range of temperatures. If it boils over a range of temperatures, as crude oil would, it's a mixture, it is not a pure substance. Back to basic chemistry then, so we're looking at periodicity. I've already told you that an atom is the smallest part of a chemical element which can exist. So what is a molecule? Well, that is two or more atoms bonded together, and the atoms could be the same element, such as H2, so hydrogen, or it could be different elements, such as carbon dioxide, but the point to notice is that with a molecule, it's just two atoms stuck together. So looking at the structure of an atom, remember that we have the nucleus in the middle, that contains the protons and the neutrons. Surrounding that we have circles which we call shells, and these are shells of electrons. Do remember when you're drawing electronic configuration diagrams that the first shell can contain a maximum of 2 electrons, and after that you can contain a maximum of 8. So let's compare the masses and charges of protons, neutrons and electrons. So protons and neutrons both have a mass of 1. So they're much heavier than electrons, and that's why we say most of the mass is found in the nucleus of an atom. An electron has a much smaller mass, and different examples will say different things, but I tend to say that it has a mass of 1 divided by 2000, so a very small number indeed. Looking at the charges now, neutron, so neutral, has no charge because it is neutral. A proton, positive, has a positive 1 charge, and an electron has a -1 charge. So when we look at an atom, we know that it is uncharged, which therefore means it must have equal numbers of electrons and protons. When we look at the periodic table, you must be really familiar with how to use the periodic table and what it's telling you. So make sure you use the key, because that will tell you which is the mass number and which is the atomic number. But generally speaking, the top number tends to be the mass number and the bottom number tends to be the atomic number. So the atomic number is actually the number of protons found in an atom. So for carbon, that would be 6. And I told you already that atoms are neutral, which means their proton number equals their electron number, which means the electron number of carbon will also be 6. And if we draw the electronic configuration diagram, we know that 2 electrons go into the first shell and the remaining 4 go into the second shell. Now looking at the mass number, now the mass number is the total number of protons and neutrons. So if carbon has an atomic number of 6, that means the proton number is 6, it has a mass number of 12, that means you can work out the neutron number by taking the atomic number away from the mass number, so the neutron number of carbon is 6. Small thing to notice is the nucleon number, and that's just the total number of particles found within the nucleus of an atom. So it's the total of the protons and neutrons, i.e. it's also the mass number, so they're very closely linked. Isotopes now, so if you look in the periodic table you will see that some mass numbers aren't whole numbers, such as chlorine, which is 35.5, and that's because chlorine exists as an isotope, which means that some chlorine atoms have a high mass number of 37 and other ones have a mass number of 35, and when you work out an average you actually find that it's 35.5, and that's because there are far more chlorine 35s compared with chlorine 37s. However, you just need to know the definition of an isotope, which is that it is atoms of the same element with the same number of protons but different number of neutrons. Going back to the periodic table then, looking at group numbers and period numbers. So the group numbers are the numbers that run along the top of the periodic table. The group number corresponds to the number of electrons in the outer shell. So group 1 elements will all have 1 electron in their outer shell. Now the period numbers run down the side and they refer to the rows. And the period number will correspond to the number of shells of electrons. Why do elements in the same group tend to have the same chemical properties? That's due to the number of electrons in the outer shell. So the answer here is because they have the same number of electrons in their outer shell. So why do fluorine and chlorine behave similarly? Because they're both in group 7 and therefore they both have 7 electrons in their outer shell. Let's look at group 0 now. What is their name otherwise known as? It is the noble gases. And why are they so unreactive? And that's because they have full outer shells, which means they don't really want to get involved in bonding. As a quick overview of the periodic table, do notice there's a step line on the right hand side, and therefore the metals occur on the left hand side of that step line, and the non-metals appear on the right hand side, with hydrogen appearing by itself at the top because it behaves very differently from all other elements. So metals now, we're going to start by looking at their properties. So remember, metals have high melting and boiling points, they're good conductors of heat and electricity, they are shiny, they are sonorous, which means when you hit it they make a noise, they are malleable and ductile. So what does malleable and ductile mean? Well, malleable means that they can be hammered into shape, and ductile means they can be drawn into a wire. Another thing to notice is stuff relating to how they bond. So be aware that when they enter into bonding, they tend to lose electrons to become positive ions. They form basic oxides, which we'll come into later, and they partake in ionic bonding. Non-metals now, their properties include the following. They are dull, so they're not shiny. They tend to have low boiling and melting points. There are exceptions to this, which we'll come on to later, but that is the general rule. They are brittle, which means when you hit them, they easily break. They form acidic oxides. They gain electrons in bonding to become negative ions, and they partake in covalent and ionic bonding. So how is an ion formed and what is an ion? So an ion is a charged particle which is formed from either gaining or losing electrons. So clearly, if they lose electrons, they lose negative charge, so therefore they become positive. If they gain electrons, they gain negative charge, so they become negative.
Let's look at ionic bonding now. So it's ionic, which means it has to be a metal and a non-metal. Use your periodic table to double check that the two things you've been given are metals and non-metals. If they're not, they're asking about covalent bonding. So let's have a look at magnesium oxide, for example. Now magnesium has an atomic number of 12 and oxygen has an atomic number of 8. So let's work out their electronic configurations. So 2 electrons go into the first shell, then they fill up to 8. So that's why magnesium is 282 and oxygen is 2.6. We only need to draw the outer electrons here, so don't worry about drawing the whole atom. So there's magnesium's 2 electrons on the outer shell. Here's oxygen's. Make sure you use crosses and dots to distinguish between the 2 atoms. There's 6, so we can clearly see where those 2 electrons will be deposited, and now we can actually draw the answer. So because magnesium's lost its 2 electrons, I'm not going to show any electrons here. Electrons have a minus charge, which is why its net charge will now be 2+, because it's lost 2 electrons. Now oxygen will have gained 2 electrons. Try and draw them a bit more circular than that, that is shocking. And I'm going to use 2 dots to represent the electrons that came from magnesium. Because it's gained 2 electrons, that's why the charge is now 2-. And therefore we can see the formula of magnesium oxide is MgO. Let's look at a different example now, which is magnesium chloride. So magnesium still has an atomic number of 12. Chlorine has an atomic number of 17. So drawing out their electronic configurations again. You can see, to be honest, the outer shell electrons from the group number. So it's up to you which way you do it. So magnesium again, 2 electrons. Chlorine has 7 electrons in its outer shell. So we can see where that first electron is going to go, but there's still a second electron here that needs to go somewhere, which is why we need a second chlorine atom. In terms of your final answer, draw magnesium. It has lost 2 electrons, which is why it's 2+. Chlorine has gained an electron from magnesium, which is why it is 1-. There are 2 chlorine atoms, so that's why I draw a second one, keeping it identical to the first one to to the first one that I've already drawn. And that's your final answer. Looking now at aluminium oxide, which is the most difficult example. So aluminium has an atomic number of 13, so its electronic configuration is 283. Oxygen has an atomic number of 8, so it's 2.6. So aluminium's outer shell will have 3 electrons on it. Oxygen will have 6 electrons. So we can see where the first 2 electrons will be deposited, which is here. But unfortunately, we've still got a leftover aluminium electron, so we need a second oxygen atom, which I'm going to draw here. You don't need these intermediate steps, by the way, if you can go straight to the answer. I'm just showing you how I found my answer out. So that's where that aluminium's electron is going to go, but that leaves oxygen still missing an electron, because now it only has 7 electrons in its outer shell. So we need a second aluminium atom, still with 3 electrons in its outer shell. So there's one of those electrons, but unfortunately we've still got 2 electrons to give away, which is why we need a third oxygen atom. And finally, it's happy, because you can see where those 2 electrons would go. And now let's actually work out what our answer will look like. I hope I've got space for this. Probably won't have. So aluminium has lost 3 electrons, so that's why it's 3 plus. We need 2 of them, which is why I'm drawing them twice. And then oxygen will therefore look like this. There's 3 of them. Let's label them as oxygen. Let's show their outer electrons. So basically they're clones of each other, they're all the same. And each oxygen gained 2 electrons, which is why their net charge is 2 minus. So actually the formula of aluminium oxide, as we can see, is Al2O3. Looking at covalent bonding now, we can see we're looking at 2 non-metals. So don't be tempted to draw an ionic bonding diagram. We're going to take a nice straightforward example to begin with, which is water, H2O. So we're going to have a central oxygen atom, 2 hydrogen atoms coming off the side, label the atoms, and then have a look in the periodic table and see how many electrons they have in their outer shell. And remember, that's given by their group number. So hydrogen has 1 electron in its outer shell. Oxygen has 6. 4, 5, 6. And now double check and see that they're both full. Oxygen now has 8 electrons in its outer shell. Hydrogen only has 2, but that's fine, because remember the first shell only needs 2 to become full. So that is now a perfectly completed covalent bonding diagram. Let's look at methane now, which is CH4, which you need to know for organic chemistry. So try and arrange this nice and symmetrically. That isn't particularly symmetrical, but it will do. So again, hydrogen has 1 electron in its outer shell, so let's start by filling in those ones. Carbon is in group 4, so it has 4 electrons. And actually that's already done, because now hydrogen has 2 in its outer shell. Carbon has 8, so that is now correct. Carbon dioxide is trickier, and I'll show you that example now. So remember, that's CO2. Remember with this one that it has double covalent bonds, and that will really help you with your answer. So carbon has 4 electrons in its outer shell, but I'm drawing it like that because I know it's a double covalent bond. Oxygen has 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And they both need to have 8 electrons to be full. So carbon has 8 electrons as 2 shared pairs, and oxygen has 8, so that is correct. The most difficult example you could be given is ethene C2H4. So I'm going to show you how to do that. There's your central carbon atoms. Here's your 4 hydrogens. Label them. It's easiest to start with the hydrogens here, remembering they have 1 electron in the outer shells. Carbon has 4, so let's make sure that hydrogen's happy first of all. So 1, 2, 3, 4. Let's do the other side. 1, 2, 3, 4. And now have a look. Yes, all the hydrogens have 2 electrons in the outer shell, and each carbon now has 8, so that is correct.
Let's now take a look at the chemical structures part of the specification, and when we're talking about chemical structures, we're talking about 4 main structures. That is giant covalent, giant ionic, giant metallic and simple molecular, and you need to know and understand why they have various properties such as either high or low melting points, electrical conductivity, that sort of thing. But we're going to start initially with giant ionic structures. So remember, these are made up of a metal and a non-metal. And what is an ionic bond? Well, it's the electrostatic forces of attraction between oppositely charged ions. So remember that the metal ion is positive and the non-metal ion is negative, and therefore they attract. So why do giant ionic structures have such high melting and boiling points? And that's because they have strong electrostatic forces of attraction between oppositely charged ions. And don't forget to qualify this by saying that they require a lot of energy to break. Why don't they conduct when solid? That's because the ions aren't free to move. Why do they conduct when they're molten or liquid? That's simply because the ions are free to move to carry the current. Why are they brittle? And don't forget that brittle means that they smash easily when hit. That's because when you hit them, or when a force is applied, the layers of ions slide, so the ions with the same charge end up next to each other. So positive charges will therefore repel and the whole structure breaks apart. So that's giant ionic done. Moving on to giant covalent, and we are really looking at carbon here. So we're looking at diamond and graphite, which remember are both forms of carbon. So your definition of an allotrope is different forms of the same element. So why does diamond have such a high melting point? And that's because it has a giant tetrahedral structure, which really means that each carbon atom is bonded to 4 others. So it has many strong covalent bonds, which require a lot of energy to break. Why does graphite have a high melting point? Similar argument, but this time each carbon atom is bonded to 3. You still have many strong covalent bonds and it still requires a lot of energy to break, but because it's bonded to 3 rather than 4 carbon atoms, that's why graphite has a slightly lower melting point than diamond. Why is graphite used as a lubricant? That's because the carbon atoms are arranged in layers with weakened molecular forces between the layers. These require little energy to break, and therefore the layers can slide off each other, hence it's used as a lubricant. Why doesn't diamond conduct electricity? And that's because it has no free electrons. However, graphite does conduct electricity, the reason being that each carbon atom, as we've already said, is only bonded to 3 others, meaning that there's a 4th electron which is free to move and therefore carry the current. We should touch on a covalent bond here. Now remember, a covalent bond is a shared pair of electrons. If you want to be more complex about it, you can say it's the electrostatic attraction between the positive nucleus and the shared pair of electrons. Why do simple molecular substances have such low melting points? And that's because they have weakened molecular forces which do not require a lot of energy to break. A small point to note, which is why do simple molecular substances have increasing boiling point with increasing MR? So remember, MR is the relative atomic mass, so it's really saying something like, why does ethane, C2H6, have a higher melting point than methane, CH4? And that's because ethane, so substances with a greater MR, have greater intermolecular forces of attraction between molecules, and these require a lot more energy to break. And remember, when you're boiling these substances, you're not breaking apart the individual atoms from the molecule, you're simply separating one molecule from another. So you're breaking intermolecular forces. Lastly, giant metallic structures. So these are just the metals you find in the periodic table. Remember, they have high melting points. That's because they have strong metallic bonds, and a metallic bond is simply the attraction between a positive ion and the delocalized electrons. So if you had to draw the structure of a metal, keep it nice and simple. Just draw a rectangle to represent the metal. Draw some positive ions evenly arranged with a sea of delocalized electrons surrounding them, and that will be sorted. Why are metals or giant metallic structures such good conductors of heat? And that's again due to delocalized electrons, what's that noise? Which are free to move and carry the heat throughout the structure. Why do metals conduct electricity? Again, that's because they have a sea of delocalized electrons which are free to carry the current. Lastly, two other properties: the fact that metals are malleable, which remember means that they can be hammered into shape, and that they are also ductile, which means they can be drawn into a wire. The reason for both of these properties is because the layers of ions can slide over each other. And touching a bit more on this, why do alloys tend to be harder than pure metals? Remember, an alloy is a mixture of metals, or something like a mixture of metals and a non-metal. So for example, steel is an alloy of iron because it contains iron and carbon. Now, why do alloys tend to be harder than pure metals? That's because the alloys have ions of different sizes, which means the layers can't slide as easily, so it's not as easy to distort the layers. Relative atomic mass I've already described a little bit, but you do need to be able to define it, and that is that it's the ratio of the average mass of an element when compared with one atom of carbon-12. I'm going to show you my favourite method of balancing equation, which always works. So if you can't actually see straight away how to balance them, use this method and you'll be able to balance any equation. So start by doing a dotted line and then list the elements present on each side of the equation, and obviously they ought to be the same. So we've got hydrogen, nitrogen, oxygen, calcium, and then just copy that straight over and line it up nicely. And now we want to do a tally chart to show how many of each element we have. So count the hydrogens on the left hand side of the equation. So we've got 1 present in the nitric acid, 2 present in the calcium hydroxide, so that's 3. The number of nitrogens is 1. The number of oxygens, well, 3 on the nitric acid side, and then you've got 1 inside the brackets, but the 2 after the brackets means that there's 2, so add those up all together and it's 5. Now the calciums is just 1. Now we need to do the same for the product side of the equation. So how many hydrogens do we have? Well, that's 2, which is present in water. Oxygen, you've got 3 present in calcium nitrate, but remember that small 2 after the brackets means that's doubled, so that's 6, plus 1 found in water, so that's 7. Nitrogen, you've got 2. In calcium you have 1, and now we need to have a look at our tally charts and see what the issue is. So the calcium are fine, the nitrogen are not fine. You've got 2 on the right hand side, 1 on the left hand side, so we're going to add a big 2 in front of nitric acid. Remember, when we're balancing equations, all you're allowed to do is add big numbers. And now readjust your tally. So you now have 4 hydrogens, 8 oxygens, 2 nitrogens. So the nitrogens are happy, the calcium is happy, but the oxygen hydrogens aren't. So I'm going to put a 2 in front of water to make that 4 hydrogens. And now adjust the oxygens. So you now have 8 oxygens. And look, the whole thing is balanced because you have 4 hydrogens on both sides, 2 nitrogens, 8 oxygens, and 1 calcium. So that is indeed balanced. Looking at more calculations now, use the formula triangle to help you rearrange, and you can see that mass is therefore given by the relative atomic mass, which is mR, times number of moles. Moles is going to be mass over mR, and that's a good way of rearranging without too much effort. So let's get started and have a look at some examples. So first of all, we're just finding the MR of calcium hydroxide, and that's just a matter of looking up the various masses in the periodic table, tends to the top number and adding them all together. So if we have a look, we see calcium is 40, oxygen is 16, but we have to times it by 2 due to this small 2 here, and then we add hydrogen, which is 1, and again times it by 2. Pop that into your calculator. And you get an MR of 74 grams. Now looking to find the number of moles in 5.4 grams of calcium carbonate. So I like to write out the equation I'm using, it's good practice. Stops you making silly mistakes. So using my formula triangle, I see it's mass divided by MR. We've been given the mass in the question, which is 5.4. Now we need to work out the MR of calcium carbonate. So using the periodic table, calcium has a mass of 40, carbon is 12, oxygen is 16, and we need to multiply that by 3 due to this 3 here.
So that's 5.4 divided by 100 of 0.054. Now we're looking to find the empirical formula of a compound which contained 22% carbon, 4.6% hydrogen and 73.4% bromine. I like to lay out these questions always using the table format. So first of all, list your 3 elements and then draw a table underneath. Mass, MR, moles, and don't forget your formula triangle. Always be aware. So remember, mass is at the top, MR and moles. And then just substitute what you know from the equation, from the question. Now notice, even though it's given percentages, because it's a ratio, really you can ignore the percentages and pretend that those are the masses, which is why I'm now going to put the mass of carbon as being 22, hydrogen is 4.6 and bromine is 73.4. Now use your periodic table to find their MRs. Carbon is 12, hydrogen is 1 and bromine is 79. And then looking at our formula triangle, we see to calculate the moles, we simply do mass divided by MR. So that's 22 divided by 12 for carbon, which is 1.83 recurring. 4.6 divided by 1 is obviously 4.6. And then 73.4 divided by 79 is 0.929113. And a note here, don't round too early because the numbers are so small, you'll introduce rounding errors. Keep them nice and long in your calculator. Then we want to divide by the smallest number. So just have a scan, and obviously 0.9 is the smallest number, so we're going to divide all of the previous answers by that number. And this is so that we have a ratio. I wish my iPad would stop deleting stuff, but it doesn't really make that much of a difference. So once you've done that, you know that will be 1. This comes out of 4.95, which I can happily round to 5 because that's basically what that number is. And this comes out of 1.98, so that's basically 2. So don't be scared to round, only if the numbers are very close. If one of the numbers had come out at 1.5, for example, so for example 1.5 versus 1, what you'd have to do in that case is double both, so you have a ratio which is 3:2. But I don't want to talk about that now because I want to finish this question. So don't forget to actually provide your empirical formula, which is C2H5Br. And that is your final answer. Sometimes they like to extend the question and tell you in part B that a different compound had a mass of 216, and then based on this empirical formula you've just calculated, work out its molecular formula. This is really straightforward. All you have to do is work out the MR of the empirical formula you've just calculated. So work that out, which would be 2 times 12 plus 5 times 1 plus 79, so that's just a basic MR calculation. Once you've done that, you see that it's 108, and compare it to the compound you've been given, which is 216. So the compound you've been given must therefore have a molecular formula which is just twice that of the empirical formula. So the actual final answer here is just C4H10Br2. If the MR of your empirical formula had been the same number, which is 216, then your answer would just have been the empirical formula, which is C2H5Br. Now I'm going to show you a water crystallization type of mole calculation. It's really similar to empirical formulae, so don't let it freak you out just because it looks more difficult. So 35.75 grams of sodium carbonate combined with water are heated strongly, and 13.25 grams remain after heating. Calculate X. So obviously after you've heated it, it will now become anhydrous, which means you've driven off the water. So lay it out like the table again, Na2CO3, but instead of listing the elements, you're just going to have the various components of the question. So it's just going to be sodium carbonate on the left, water on the right, and then mass, MR, and moles as usual. So we know that 13.25 grams of the sodium carbonate remain after heating, which is why this is the number here. Going to have to do a small calculation to work out the amount of water that was lost. So that's 35.75 minus 13.25 to get 22.5. The MR, use the periodic table, so we'll see sodium is 23, times it by 2 because of that small 2, plus carbon's 12, plus 3 lots of oxygen, which is 16, to get an MR of 106. And I know off by heart that the MR of water is 18, and you can check that in the periodic table if you don't believe me. To work out the number of moles now, mass divided by MR, giving us 0.125. This is 1.25. And then divide by the smallest number, which is clearly 0.125. So that will obviously be 1. This is 10. Therefore, x equals 10, and that's it. It's very similar to the empirical formulae question. Now we need to look at reacting mass and gas volume questions. So 3.3 grams of hydrochloric acid react with sodium carbonate. Calculate the mass and volume of carbon dioxide collected. Now, I do imagine that in your question paper they'll give you the balanced symbol equation, which is the starting point of this calculation. However, in another part of the exam paper, they could easily expect you to write out your own salt equations and to balance them, which is why I'm going to do all of that right now. So hydrochloric acid reacts with sodium carbonate to produce a salt, which is sodium chloride, plus water, plus carbon dioxide. Make sure it's balanced. I know I need a 2 there and a 2 here. And now we need to use the table format in order to help us answer the rest of the question. So mass, MR, and moles. And don't forget to use your formula triangle down here, which is mass, MR, moles. And this is how I always set myself up to make sure I'm going to get the question right. So what have we been given in the question? Well, we know 3.3 grams of hydrochloric acid reacted, and we know we need the volume and mass of carbon dioxide, which is why my x goes here. Now the MR, use the periodic table. Now make sure you're just adding up the hydrogen and the chlorine. You're not including the 2 in this. So it's just 1 plus 35.5 equals 36.5 grams. The MR of carbon dioxide is going to be 12 plus 2 lots of 16, which is 44. Using the formula triangle, we see that moles is mass divided by MR. So we do 3.3 divided by 36.5 to give us 0.09044109. And now remember, what we can do here is carry that number across to be the number of moles of carbon dioxide. Do check the big numbers up here. Now there's 2 lots of hydrochloric acid compared with only 1 lot of carbon dioxide, which is why in order to carry over the moles we have to actually divide 0.09041 by 2. And that becomes 0.045205. And now we're ready to work out the unknown mass of carbon dioxide, which is mass equals MR times moles. We've already calculated the MR, which is 44. Moles is 0.045205. And that is 2 grams to 3 significant figures. Why is it so noisy in London everywhere? Now to make sure we're answering the second part of the question, which is to do with gas volumes, make sure you know that 1 mole of any gas occupies 24 decimeters cubed. So we know the number of moles of carbon dioxide. We've already calculated that, which is 0.045205. Therefore, to work out the volume, simply times that by 24. Becomes 1.08 decimeters cubed. So that's the answer to the second part of the question. Do notice that they could have asked you it in terms of centimeters cubed, and in order to convert decimeters cubed to centimeters cubed, you just have to times by 1,000. So just times that number by 1,000, and therefore your answer here is
1080 centimeters cubed to 3 sig fig.
3.2 grams of copper reacted with 0.4 moles of nitric acid. Which reagent is in excess? Don't worry too much about this. We're going to use the same method as always, which is the table format. So we're going to write mass, MR and moles down the left hand side. And remember our triangle, which I'll put here, which is mass at the top, number of moles and MR. So we know that 3.2 grams of copper reacted. And weirdly, we're going to put X here because that is important, and I'll say why soon. So first of all, what is the MR of copper? Using your periodic table, you see it's 63.5. So using your formula triangle, how do you work out the number of moles? You do mass divided by MR, so that's 3.2 divided by 63.5 to get 0.05 mole. And then have a look at the big numbers. We've got an invisible 1 here, we have a 4 here, and I've already taught you, you just need to pull that number across, but instead times it by 4, so you get 0.2 moles. So now we compare, we have a look, and we have a look at what we were given in the question. Well, we were told we had 0.4 moles of nitric acid, but we only need 0.2, so clearly nitric acid is in excess. Now we're looking at percentage yields. So for example, in a reaction, 11.2 grams of copper sulfate was obtained when theoretically 12.5 should have been obtained. Calculate the percentage yield. So you just need to use this equation here, which is percentage yield equals actual yield over theoretical yield times 100. So the actual yield here was 11.2. The theoretical one was 12.5. Multiply it by 100, and you get a value which is 89.6%. Now they can be more difficult than this, so I'm going to show you that example now. So let me talk you through a slightly more complicated version. So a student reacted 2.4 grams of copper oxide with sulfuric acid. She made 1.8 grams of copper sulfate. Calculate the percentage yield. So as always, we need to start with a balanced symbol equation. So that will be copper oxide plus sulfuric acid, which is H2SO4, forms copper sulfate, CuSO4 plus water. And then step back and double check that it is balanced, and it is. And we're going to use my favourite table as well, obviously, because I never do a mole calculation without it. So let's start with what we know. We know that we have 2.4 grams of copper oxide, and we have made 1.8. So that is the actual yield, and we need to find out the theoretical yield, which is why I'm going to put an X here. So now it's just a matter of working out the MR of copper oxide. So do 63.5 plus 16. So use your periodic table for that to work out that its MR is 79.5. To work out the number of moles, simply do the mass divided by the MR. So that's 2.4 divided by 79.5 to give a value which is 0.0302 moles. Now we need to look at the balanced symbol equation and have a look if there are any big numbers. There aren't, so we can easily just carry that number across to be the number of moles of copper sulfate. Now work out the MR of copper sulfate. So you want to do 63.5 plus 32 plus 4 times 16. So that gives us an MR which is 159.5, and then we work out X by doing 159.5 times by 0.0302 to get 4.8169 grams. And now we can just substitute that into our percentage yield equation because that is the theoretical yield. So percentage yield is given by actual yield over theoretical times by 100 because we're looking for a percent. So actual was 1.8, theoretical was 4.8169, times that by 100, and we get a value which is 37%.
Let's look at titration calculations now. So 25 centimeters cubed of 2 mole DM to -3 hydrochloric acid reacted with 30 centimeters cubed of sodium hydroxide. Calculate the concentration of sodium hydroxide. You need your balanced symbol equation for this, which again I think they'll give you, but you do need to be able to do this as a separate skill, which is why I'm going to do it now. So the salt made is sodium chloride and water is the byproduct. Double check to see if it needs balancing, and it doesn't. And then to be clear, make sure you use this formula triangle now, which is number of moles goes at the top, concentration and volume go at the bottom, and therefore titration calculations will be really straightforward for you.
So just make sure in your table this time it goes moles, concentration and volume, and then substitute in what you know from the question. So your concentration of hydrochloric acid is 2 moles dm to the minus 3, so that's going to be 2. The volume we've been told is 25. Now, to make sure you don't screw up these questions, make sure you convert that straight into decimeters cubed. So I do that by just writing divide by 1,000, so I know what to put into my calculator. We know the volume of sodium hydroxide is 30, so I'm going to do the same here. Make sure I've divided it by 1,000 in order to account for the fact it needs to be in decimeters cubed, and then we're looking for the unknown concentration of sodium hydroxide. So the moles is concentration times volume. I can see that from the formula triangle. So let's work out the number of moles of hydrochloric acid. So 25 divided by 1,000 times 2, which is 0.05. Have a look at any big numbers. There aren't any, so that means I can carry that number straight over, and that becomes the moles of sodium hydroxide. To work out this unknown concentration, we have to do moles divided by volume. We can see that from the formula triangle. So we do 0.05 divided by 30 over 1,000. Just pop that all into your calculator as it is. And you get an answer which is 1.6 recurring. So that rounds to 1.67 moles dm to the minus 3 to 3 sig fig. Unfortunately, there are some ions which you'll simply have to learn off by heart because you can't work them out from the periodic table. So let's just go through what all of these are. Starting with these transition metals along here, just going to have to learn them. The first one is silver, this one is copper, Pb2+ is lead, and zinc is Zn2+. Notice with transition metals like iron that have variable valencies, you'll be given it in the question so you can actually see what their charge will be given by the Roman numerals. So that's not something you need to remember. This is the ammonium ion. And now looking at the negative ions, if it's combined with oxygen, it tends to have 8 in its name. So this is carbonate, sulfate, and nitrate. And that final ion is hydroxide. So now we can get started on some examples. So starting with magnesium chloride, so let's write down the ions. We can see from the periodic table that magnesium is in group 2, hence Mg2+. Chlorine is in group 7, so 8 minus 7 is 1, hence Cl-. Now have a look, they're not balanced obviously. You've got a 2+ and a 1- charge, so clearly you need 2 chlorines. Remember, when you're writing the formula, you write a small number after the element in question, which is why this is the formula of magnesium chloride. So lead hydroxide, these are both ions you're going to have to learn off by heart. So Pb2+, OH-. So we've got the same issue here in that we don't have enough minus, so you need 2 OHs. So you're going to write PbOH2. However, the 2 applies to both the oxygen and the hydrogen, which is why you need brackets. So insert brackets, and that is your formula. Now lithium. Lithium is in group 1, so it has an Li1+ charge. So it has a 1+ charge. Oxygen is in group 6. 8 minus 6 is 2, so it's O2-. This means you need 2 lithium for every oxygen, so Li2O. Magnesium nitrate. Magnesium is in group 2, so Mg2+. Nitrate you've got to learn from the list above, NO3-. You've got a 1- charge with nitrate compared with the 2+ charge on the magnesium, which explains why you need 2 lots of that nitrate, and you need to insert brackets again. Don't touch this 3 here, that just remains part of the formula. People get confused and start moving it around. No, that is the final answer. Lastly, aluminium in group 3, 3+. Learn sulfate's charge, which is SO4 2-. This is a difficult one now. It's not that clear. You've got to find a common number that both 3 and 2 go into, which is 6. So if I show you my thought process, I effectively need 2 aluminiums and 3 sulfates to make it equal 6, because now we have 6+ on the aluminium side, 6- on the sulfate side. So that's therefore Al2 SO43, not forgetting the brackets as usual. Now, if you don't like the method I just showed you, there is a cheats way of doing it where you don't actually have to understand the chemistry. What you do is you write out the ions as usual, so potassium is in group 1, hence 1+, oxygen is in group 6, 8 - 6 is 2, so 2-, and all you have to do here is swap and drop. So literally bring down that invisible 1 to here, that 2 to there, and then rewrite the ions. So your final answer is K2O. And it works with anything really. So let's do aluminium nitrate. Aluminium's in group 3. Nitrate we've learned off by heart from the list above. We're going to swap and drop, so we're going to bring that 3 down. We're going to bring that invisible 1 down. And so it becomes AlNO3, 3, because you brought that 3 down.
And in electrolysis, remember you have your giant ionic structure. It needs to be molten or in solution. Why? To allow ions to be free to move so they can carry current. That is essential. So if you have solid sodium chloride and you attach the electrodes to it, you're not going to be able to conduct electricity through that sodium chloride. We've just discussed this in chemical structures because the ions aren't free to move. Putting it in solution means that the ions are free to move, so we can carry a current. So those 2 electrodes dip into the substance. Now remember, the electrodes are made out of an inert substance, and that means an unreactive one, which makes sense. You don't want it getting involved in the reaction. So they can be made out of things like platinum or graphite, as these are unreactive. In terms of naming things properly, you've got to remember what an anion and a cation is. So cations are positive ions, anions are negative ions. So remember, opposites attract. So anions, which are negative, will be attracted to the anode, which is positive, and the cation, which is positive, will be attracted to the cathode, which is the negative electrode. So do try and remember that, and I always use PANC to help me remember. Positive anode, negative cathode. Anodes attract anions, cathodes attract cations. So the ode ending is the electrode and the ion is the ion. In terms of remembering what forms where, you need to remember a few rules. So if you have aqueous solution, that makes it more complicated, because as well as, let's take sodium chloride for example, so as well as the sodium and the chloride in solution, you've got hydrogen ions and hydroxide ions, and remember only one of those ions can move to each electrode. So let's take the negative electrode first of all, which is the cathode. That is obviously going to attract a positive ion because opposites attract. Now in order to work out which ion it attracts, remember it is the least reactive element that discharges at the negative electrode. So in the case of sodium chloride with hydrogen and hydroxide, that will be hydrogen, so H+ ions will discharge. And when you're writing these equations, remember you've got H+, you're trying to make it neutral, which is why you have to add E-, you have to add electrons to it, and it will form H2, because remember hydrogen is diatomic. Because you've added electrons, remember this is reduction, so don't forget oil rig. Oil rig is a way of remembering the difference between oxidation and reduction. Oil, so oxidation is loss of electrons, reduction is gain. So in the case of hydrogen, you've got a gain of electrons, so reduction. Now looking at what discharges at the positive electrode, make sure you remember that halogens discharge before anything else. We have a halogen in solution here, a halide ion. It's chlorine, so chlorine will discharge. So Cl- will have to turn into Cl2. The easiest way to see what will happen is, because it's minus and you need it to become neutral, you need to remove the negativity, which is why you need to remove E-. Because you've lost electrons, you've therefore carried out oxidation. And you must practice lots of these questions because this is really quite tricky. Do notice that both hydrogen and chlorine are both diatomic molecules, so you'll be making H2 and Cl2. And remember the other elements which are also diatomic is nitrogen, chlorine, fluorine, bromine and iodine, and oxygen. Now do remember this as a list, because in case it comes up and you've got to balance equations, you've got to remember that they're diatomic. And my friend who's also a teacher, she told me a way to remember this, which is horses need oats for clear brown eyes. So hydrogen is horses, need is nitrogen, oats is oxygen. For is fluorine, clear is chlorine, brown is bromine, and eyes, it's a bit strange because obviously it's not eyes, it's about eyes, but iodine. Going back to our aqueous sodium chloride example, so I've already told you that hydrogen discharges, chlorine discharges, so left over in solution you have sodium hydroxide, and this is actually a very important industrial process because all three of these products are very useful. Why? Because chlorine is obviously used as a disinfectant. It helps to kill bacteria in drinking water and swimming pools, for example. Hydrogen can be used as a fuel. It's also used to harden vegetable oils to make margarine. And sodium hydroxide is used for making bleach and for making paper.
So we've looked at electrolysis in a lot of detail now, but we're going to go through some various examples and try and work out what is made at the anode and what is produced at the cathode, together with some observations. So let's do this as a table. So don't forget that your anode is positive and your cathode is negative, and I've written those there so we know what's going on. So we've got molten lead 2 bromide to begin with. And remember, that's therefore going to be made up of Pb2 plus and Br minus. And that 2 here has told us that it's 2 plus. Bromine is in group 7. 8 takes 7 is 1, hence why its charge is -1. So remember that opposites attract, which therefore means that at the anode you're going to produce bromine and at the cathode you're going to produce lead. The observations here are that the lead collects at the cathode and it literally just drips off in a molten state, whereas bromine gas is produced at the anode, which bubbles off. Our next example is going to be concentrated hydrochloric acid. What are the ions involved again? That's H plus and Cl minus. Again, opposites attract, which means that at the anode we're going to have chlorine produced. At the cathode we'll have hydrogen. These are both gases and they'll both be bubbled off. Next up, we've got aqueous sodium chloride. This is becoming more complicated now because it is aqueous, so we need to list the ions involved. So because it's aqueous, we have H plus, OH minus. The sodium, well, that's in group 1, so we have Na plus. Chlorine is in group 7, 8 takes 7 is 1, so it's Cl minus. And then when we come to look at the product at the anode, remember only one product can be formed. And at the anode, you're going to find that the halogen wins in every single case. The halogen here is group 7, which is why chlorine is produced here. The product at the cathode, where you're looking for the least reactive element out of the positive ions. So we're looking at hydrogen and sodium. Clearly, hydrogen is far less reactive than sodium. Sodium is an extremely reactive group 1 metal, which is why we're going to have hydrogen produced here. The chlorine and hydrogen will be bubbled off, as with the hydrochloric acid example above. Electroplating now, and that's where you cover an object with another metal. You need to know a few things here, which is that first of all, rather than using platinum or carbon as the anode or cathode, what you're going to do here is use the metal that you're coating your object with as the anode. Object being coated or plated is your negative cathode. The electrolytes, so the substance undergoing electrolysis, is actually a solution of a soluble compound of the metal. And when electrolysis occurs, what you find is the metal ions are reduced at the cathode. So for example, if we were coating in copper, they would be reduced, which means they gain electrons at the cathode to become copper solid. And as a result, that cathode becomes plated or covered in that ideal metal, which in this case would be copper. So let's look at some uses of electroplating. And really it's because electroplating objects gives them much better properties compared with usual, or it means it's cheaper to have a particular object. So famously, lots of jewellery is electroplated. So things, if you buy a necklace and it says that it's silver plated, that has undergone electroplating. And you tend to find that the actual necklace itself is made out of copper, and then it has a very thin layer of silver over the top. So why would we want to do that? Well, because silver is exceptionally expensive. It's very rare. There isn't very much found within the Earth's crust. Copper is way cheaper. So if you make the bulk of the necklace from copper, add the silver plate, you get the same effect. Obviously, the quality won't be the same. We also coat steel bumpers, so that's a part of a car, with chromium. Chromium is very hard and very shiny, so it's aesthetically really pleasing. It's got great properties, but it's very expensive, hence why we don't make the whole object out of chromium. Lastly, we coat cans or tin cans which are made out of steel. So a saucer can that you get baked beans out of or something, it will mostly be made out of steel, but it'll have a coating of tin on it because tin is corrosion resistant and won't react with the food contents, which we really don't want to happen, obviously. Let's look at electrolysis in copper refining. So that basically means purifying copper. So what you have here is you have your positive anode, which is made out of impure copper. Your negative cathode is made out of pure copper. And then you have an electrolyte, so the substance undergoing electrolysis, which is copper sulfate. So clearly you're going to have Cu2 plus ions in solution and SO4 minus. And what you find here, as you would expect, is the opposites attract. So that Cu2 plus is attracted to the negative cathode and it undergoes reduction, which means it gains 2 electrons to become solid copper. As the solution gets used up, what you find is that the impure copper at the positive anode dissolves. So effectively it adds more copper ions to the solution, and then this is a continual process whereby those copper ions which are added to the solution are attracted to the negative cathode, where they become reduced and gain electrons, and as such the copper becomes purified. Do notice lastly that there are impurities which collect at the anode which drop to the bottom of the electrolysis chamber. In terms of what you see as an observation, just remember that copper sulfate is this beautiful turquoise blue colour. Now, as that cathode becomes coated with copper, you'll see a lovely bronzy colour form at the cathode. It's like an orangey bronze colour, which will obviously be the copper forming. And as a result, you see a loss of blue colour, as you have less copper sulfate. So remember, a cell is an object which can produce electrical energy. You do need to know that a simple cell is actually made out of 2 metals and an electrolyte. A redox reaction takes place, which is where reduction and oxidation occur at the same time. And while this is taking place, an electric current is formed. So I thought the easiest way to talk you through the energetics topic was to take you through some past exam questions because they're pretty much all the same. So the moment you see a polystyrene cup and a thermometer, we're looking at enthalpy. So be aware of what endothermic and exothermic means here. So remember, exothermic means gives out heat energy and endothermic means takes in heat energy, and with an exothermic reaction you're looking for a negative delta H, whereas endothermic you're looking for a positive delta H. Again, in terms of the actual temperature of the beaker or the cup, an exothermic reaction will get hot and an endothermic one will get cold. And if you bear that in mind, hopefully it'll make answering these questions far more straightforward. A student uses this apparatus to investigate the heat energy released when nitric acid is added to potassium hydroxide solution. So we've got nitric acid inside the burette, which is going to be dripped into the polystyrene cup containing potassium hydroxide. She uses this method. Put 25 centimeters cubed of potassium hydroxide solution into the polystyrene cup. Measure the temperature of the potassium hydroxide solution. Add 5 centimeters cubed of nitric acid from the burette. Stir the mixture and measure the highest temperature reached. Add further 5 centimeters cubed samples of nitric acid. Stir and measure the highest temperature reached after each addition. Name the piece of apparatus that should be used to measure the 25 centimeters cubed of potassium hydroxide solution. So you need a fairly precise piece of apparatus here, which is why you should state either a pipette or a burette. Measuring cylinder would not be precise enough. The table shows the student's results. So here she's got the different volumes of acid and the highest temperature reached, and we can see the highest temperature was reached when the largest volume, 30 centimeters cubed of acid, was added. The result for 20 centimeters cubed is anomalous. Suggest two possible mistakes other than misreading the thermometer that the student might have made to produce this anomalous result. So remember, anomalous means that it's the odd one out. It isn't quite what you would expect, and if we actually look at those results, it's 31, which is pretty close to 29. So we're thinking that the temperature is too low. So what could have caused the temperature to be too low aside from misreading the thermometer? Well, first of all, she could have added less than 5 centimeters cubed extra of the acid. Secondly, she might not have waited until the highest temperature was reached. And thirdly, remember when you're doing this experiment, it's really important that you stir the reactants. So she might not have stirred them properly. Suggest a true value for the temperature when 20 centimeters cubed of acid is added. So let's have a look. You kind of want somewhere that sits between 29 and 37. So I'd probably go in at 33. In another experiment, the student records these results. Volume of potassium hydroxide solution, starting temperature of potassium hydroxide solution, total volume of acid added, and the highest temperature reached by the mixture. And we're calculating the heat energy released using this equation, Q equals mc delta T. So this is really nice. They've given us pretty much all of it. So Q is what we're after. Mass of the mixture, so you need to add those two volumes together. So 25 plus 25 is 50. Times the specific heat capacity, which we've been given, is 4.18, times the temperature change, which is, we know it goes from 16 to 35, meaning that there has been a 19-degree increase. And then when you pop that into your calculator, you get a value which is 3970 to 4 significant figures. Let's have a look at some more questions. So explain in terms of making and breaking bonds why some reactions are endothermic. Draw a labelled energy level diagram for an endothermic reaction. So this is what you need to do. You need to do your axes here. The y-axis is the energy, and the x-axis is basically the progression of the reaction. So remember, with endothermic, you're looking at a positive delta H, which means that the products by definition must sit at a higher energy level than the reactants. So make sure they are, and then we label them products. We've got our reactants over here. And then just draw an arrow from the reactants to the products going upwards, so delta H is positive. Use the bond energy data to calculate the enthalpy change for the reaction below, making sure to give a sign and units in your answer. Draw a labelled energy level diagram for this reaction. 5 marks. Okay, so this is good. If they haven't drawn them out for you like this, you need to see all the bonds. Make sure you draw out that diagram, otherwise you'll screw up. So it's so important that if they give you it looking like this instead, like CH4 plus 3O2, it is essential that you convert it into a picture like this. So let's have a look at the bonds broken first of all. And so just start by listing the bonds. So we've got CH, and how many do we have? Well, we've got 1, 2, 3, 4, and I do like to cross them off just to make sure I've got them all. Then look into the table, and it's 4, 1, 2. Then we've got 1 C bond, which is 6, 1, 2. And then we've got 3 lots of the oxygen, so that's 3 times 4, 9, 6. Use your calculator to add it all up. These questions are just about being accurate more than how difficult they are. So you must check your answer. So that's 3, 7, 4, 8. Now bonds made. So be careful here. We've got an OC bond, and count how many there are. There are 1, 2, and then there's a big 2 there, which means there's 4 times 7, 4, 3, which I've got from the table again. And then again with the OH, we've got 1, 2, and then the 2 again, so it's 4 times OH. So 4 times 4, 6, 3. And that gives us 4, 8, 2, 4. And then in order to work out this, you need to do 3, 7, 4, 8. Take away 4, 8, 2, 4 to get minus 1076 kJ mole to the minus 1. Be careful with your units. And that reaction is therefore exothermic because it's a minus. Just to show you how to draw the energy level diagram, really similar to what we did above. Here are our axes. We've got energy or enthalpy on the y-axis. Now do remember, because it's exothermic, that our products therefore have less energy than our reactants, which is why it's this way around. We know the arrow is going to go down, and it's by minus 1076 kJ mole to the minus 1. And then just label your reactants. And you can be really precise here because you can actually see what the reactants are. So I'm just going to write C2H4 plus 3O2 as the reactants. And then I can see that the products are 2CO2 plus 2H2O. So we know all about fossil fuels as a method of producing lots of energy, but we're looking for cleaner fuels, and one particular fuel we're very interested in is hydrogen. So the reason we're very keen on this as a possible source of energy is because, first of all, it's exceptionally available. It comes from seawater. The reaction that takes place is actually hydrogen reacts with oxygen, forming water. Let's balance this equation. This is a great thing to happen because water is not a pollutant. We need to drink it every day to keep ourselves alive. It's a very clean byproduct, unlike the carbon dioxide, carbon monoxide that comes from burning fossil fuels. This process is going to be carried out using a hydrogen fuel cell. And what you find is that hydrogen is oxidized at the negative pole, which means that it loses electrons. And then conversely, you find that oxygen is reduced at the positive pole. So we're going from oxygen gas to the ion, which is O2 minus. It's reduced, which means it needs to gain electrons. And now we need to balance our oxygens. Because oxygen is diatomic, we need a 2 here. It's reduced, which means it gains, and we need a 4E minus there. As an alternative to fossil fuels and hydrogen, we can use nuclear energy. And that obviously involves the use of radioactive fuels such as uranium-235. Now, we need to know a lot about this in physics. It's all to do with nuclear fission. Really, for chemistry, you just need to know that when nuclear fission takes place, you generate a lot of thermal energy, which is used to heat water to produce steam. Steam turns the turbine, and the turbine turns the generator, and a generator is a machine which generates electricity, as the name suggests.
Now we're moving on to rates of reaction. So looking at the effect of temperature, surface area and concentration on rates of reaction. So what effect does increasing the temperature have on the rate of reaction? Well, clearly it's going to increase it. The reason why is because particles have greater kinetic energy, so they collide more frequently. The collisions are harder, and therefore a greater proportion of these collisions result in the required energy to overcome the activation energy. Looking at concentration now. So if you increase the concentration of particles, that means that there are more particles in the same volume. Clearly, collisions will occur more frequently, and therefore the rate of reaction will increase. Surface area now. If you increase the surface area, for example by powdering marble chips, powdered marble chips have a larger surface area than giant lumps. And so by increasing the surface area, you're ensuring that you have an increased frequency of collisions, and therefore the rate of reaction will increase. And do make sure you can argue this from if you decrease the surface area, decrease the concentration and decrease the temperature. You just need to say the exact opposite. Remember, there are several ways in which you can measure the rates of reaction. So rates of reaction are given by, for example, a change in volume over time, a change in concentration over time. Now, if we use the marble chip example, remember that marble chips, when reacted with hydrochloric acid, they will produce carbon dioxide. So you can measure how quickly that carbon dioxide is produced, either using a top pan balance. Now remember, that needs a high resolution because carbon dioxide doesn't weigh very much, so you need at least like 0.00 on your weighing scale in order to measure that difference. So when it escapes out the top of a conical flask, you'll see the mass decreasing, and you can measure that over time. Equally, you could use gas syringes, and that will show you the volume of carbon dioxide that's released. You can't use this method if you're measuring hydrogen gas because it is too light, so you won't actually be able to see a change in the reading on the measuring balance. Sometimes there are experiments involving crosses being obscured due to a precipitate being formed, so you measure the time taken for the cross to disappear, but that's obviously fraught with difficulties because it's very much human judgment as to decide when that cross disappeared. So do be prepared to talk about some limitations related to the methods used.
So we need to look into the rates of reaction, chemical reactions topic in slightly more detail. And luckily it's not difficult, it's more just stuff you're going to have to rote learn, so learn off by heart. So the first point is to do with dangers. So why are fine powders an explosion risk in industry? So why does the use of fine powders mean that theoretically the factory could blow up? And our example we want to look at here is in flour mills. So a flour mill is somewhere where you take wheat, you grind it up to produce flour that you can bake bread or bake cakes with. So what you find here is obviously with the flour, you have very small particles. And as we've just learnt in rates of reaction, very small particles have a very large surface area. Coupled with that is that these particles are flammable, which means they set alight easily. And that means that if these happen to catch fire, you have an extremely high rate of reaction due to the large surface area of those flour particles, meaning that the whole flour mill is liable to explode due to a massive fire. Now looking at similar risks in coal mines. So remember, coal mine is somewhere that you dig coal out of the ground, which is carbon, used in the blast furnace, so you burn stuff with it. Now this is an extremely dangerous place to work because what you find is there's a lot of methane gas, remember that's CH4, in the air. And we know from the crude oil topic that this is used as a fuel. So you've basically got all this vaporized fuel in the air, which is extremely flammable. And if there's a single spark, that can lead to an enormous explosion, making it a very dangerous place for the coal miners to work.
Now we're looking at equilibrium. So with the term exothermic, let's define it. First of all, it means the release of heat energy. And remember that more energy was needed to make the bonds in the products then was needed to break the bonds in the reactants. So looking at endothermic reactions, you'll see the opposite. So heat energy in this case is taken in, and more energy is required to break the bonds in the reactants than was needed to make the bonds in the products. Other terms we need to know: activation energy. This is simply the minimum amount of energy required for a reaction to occur. How do catalysts work? Well, we know from biology that they speed up the rate of reaction without being used up. In terms of how they work, it's because they provide an alternative reaction pathway with lower activation energy, and I'll show you some energy profiles so you can actually see that lowered activation energy. So chemical equilibria now, we are looking at reversible reactions here, so be aware of this special arrow. This is your reversible arrow, and it tells you that the reaction is happening in both the forward and backwards direction, and what that really means is the reactants react to produce the products, as we're used to seeing, but then the products will fall apart effectively and produce the reactants again. So these aren't ideal conditions when we're talking about industrial processes, because it basically means you make very little of the product that you're after, and we use the word yield to describe the amount of product produced. So let's start by looking at what a dynamic equilibrium means. Now, first of all, the word dynamic means that the reactions are ongoing, which means that the forward and reverse reactions are occurring at the same time. Because it's equilibrium, it means they're occurring at the same rate, and that there is no overall change in the concentrations of reactants and products. And this is only true if it occurs within a closed system, and a closed system is simply one where nothing is allowed to escape. So no gases can leave and no more reactants get added. It remains a sealed vessel. So looking closer at dynamic equilibria, let's look at the effect of a catalyst. Now, you must notice that a catalyst simply increases the rate of reaction. We know this, I've just said it. It does it by providing an alternative reaction pathway with lower activation energy. Note, it does not alter the position of equilibrium, so it doesn't increase the yield of the products. It keeps the position of equilibrium in the same place, it just increases both the forward and reverse reactions equally. A summary now of what happens when we choose to alter reaction conditions. So remember, we can alter the position of equilibrium if we change both the temperature and pressure. As I've already said, the catalyst has no effect. Remember, when a reaction is exothermic, the whole reaction gets hotter, and when it is endothermic, the whole reaction gets cooler. So if we start by increasing the temperature, we know we need to oppose the change, so we're going to favour the reaction, which results in a decrease in temperature, which is why increasing the temperature favours the endothermic reaction. And that means that the position of equilibrium will shift to favour that endothermic reaction. So if you have an equation and the delta H says that it is positive, we know that the forward reaction is therefore endothermic. So increasing the temperature will favour the forward reaction. Decreasing the temperature will favour the exothermic reaction, and the position of equilibrium will shift to favour that. And if this is sounding complicated, don't worry, because we're going to use the Haber process as an example to help us understand it. Looking at pressure now, if you increase the pressure, what happens is equilibrium position will shift to favour a decrease in pressure, so it will shift to the side with a fewer moles of gas, and you count the number of moles by looking at the big numbers in front of the formulae. Decreasing the pressure will favour the side with increased number of moles of gas, so position of equilibrium will again shift. So the Haber process, this is the manufacture of ammonia, and it involves the use of nitrogen and hydrogen. Delta H is negative, which means the forward reaction, the reaction which produces ammonia, is exothermic. So in order to increase the yield of ammonia, it makes sense therefore that we decrease the temperature. Why? Because the forward reaction is exothermic, so the position of equilibrium will shift to the right, and therefore more ammonia will be made. However, the problem with low temperatures is it's all to do with collision theory, means that the particles have very little kinetic energy. So although when they collide, a reaction takes place, the likelihood of them colliding is now very low because of the low temperatures, which is why we actually have to increase the temperature to 450 degrees Celsius, and we therefore call these conditions compromised. Looking at the pressure now, if we count the number of moles of gas by looking at the balanced symbol equation, you can see that there are 4 moles of gas on the left hand side and 2 moles of gas on the right hand side. So in order to increase the yield of ammonia, we need to increase the pressure, because remember, increased pressure will favour the side with fewer moles of gas. Therefore, the position of equilibrium will shift to the right, meaning that more ammonia is made. Now again, this is a compromised condition because although the high pressure will favour increased yields, unfortunately high pressures are expensive and they are dangerous because the reaction vessel needs reinforcing, and therefore we used a compromised pressure of 200 atmospheres. We do add an ion catalyst when we're talking about ammonia. The addition of the ion catalyst increases both the forward and reverse rates of reaction, but it has no effect on the position of equilibrium, and therefore it has no effect on the yield of ammonia. Let's look at another example now. So I'm going to bring up an equation which is showing NO2, reversible arrow, and N2O4, and do notice their colours. NO2 is brown and N2O4 is colourless, and look at the delta H sign, it is an exothermic reaction. So let's see what happens when we increase the temperature. So what happens when we increase the temperature is the endothermic reaction will be favoured, which means the reverse reaction will be favoured. So the position of equilibrium shifts to the left. You therefore make more NO2, and so therefore the colour changes and it becomes brown. Looking at pressure now, and we are going to increase the pressure. So let's compare the number of moles of gas on both sides of the equation. You can see that there are 2 NO2s and only 1 N2O4, so increasing the pressure will favour the forward reaction, so the position of equilibrium shifts to the right, and therefore more N2O4 is produced, so the colour will change to colourless. So be prepared to talk about what effect various changes in pressure and temperature will have, and again notice catalysts have no effect. Let's remind ourselves of the definitions of oxidation and reduction. So oil rig, oxidation is the loss of electrons and reduction is the gain of electrons. Redox now, and that, as the name suggests, is a reaction where reduction and oxidation occur at the same time. A reducing agent is a substance which causes another substance to be reduced, so it forces the other substance to gain electrons, and therefore by definition a reducing agent is therefore oxidized. An oxidizing agent causes a substance to become oxidized, so it forces the other substance to lose electrons, and therefore by definition an oxidizing agent is reduced.
Let's look more closely at the topic of acids, bases and salts. Now, first of all, we need to start by listing the properties of acids. Now, we know an acid donates hydrogen ions. It has a pH of less or equal to 6, because remember pH 7 is neutral. And because of this low pH, remember it turns litmus paper, which is a type of indicator to show how acidic or alkaline a substance is, and that will turn red. Similarly, universal indicator will turn red in a strong acid, orange in a weaker acid like a medium acid, and yellow in a weak acid. You need to be very clear on the reactions, which I'm going to go into in more detail, but just to summarise here, if you have a metal and an acid, you produce a salt and hydrogen. I promise I'll show you examples including actual metals. If you have either a metal oxide or hydroxide plus an acid, you produce a salt plus water. And then lastly, metal carbonates plus acids form a salt plus water, and the carbonate indicates that you'll produce carbon dioxide. The last indicator I meant to mention, which I probably should further up, is to notice methyl orange handily also turns red in the presence of acid. Let's look at bases now. Remember that these are hydrogen ion acceptors. Again, we need an in-depth knowledge of the colour that all the indicators turn. Remember that a base has a pH greater or equal to 8, so they will turn universal indicator blue or purple. Litmus paper, again, will turn blue. Methyl orange, unluckily, doesn't turn blue. It turns yellow. Now, in terms of their reactions, you need to remember that a base reacts with an acid to form a salt plus water. And lastly, notice the difference between an alkali and a base. And really, the only difference here is that an alkali is a soluble base. So if we do a little Venn diagram, you'll find that all alkalis are bases, but that not all bases are alkalis. Let's look at the difference between strong and weak acids. The crucial thing here is that in a strong acid, remember it contains lots of hydrogen ions, and what you find is that they readily dissociate. And what that really means in layman's terms, if you have hydrochloric acid, that is a strong acid, and it will extremely easily give up all of its hydrogen ions, or pretty much most of them. Whereas with a weak acid, you find that the hydrogen ions don't readily dissociate. They don't enter the solution easily, and they stay combined with their other ions. So something like ethanoic acid, which is a carboxylic acid, we call this a weak acid because it doesn't give up its hydrogen ions easily. And remember that acids in solution can carry a current, and that's due to the presence of the hydrogen ions. Clearly, with a strong acid, there are more hydrogen ions, so the solution can carry more current than compared with a weak acid. And more easy to understand is the fact that you will see a lower pH with a strong acid, so of approximately 2 maybe, whereas a weaker acid, you'll see a much higher pH of approximately 6. Looking at the bases now, so the strong and weak bases, luckily it's incredibly similar to what we've just learnt with the acids. So you can pretty much say the same thing, which is that a strong base will readily dissociate. A weak base will not readily dissociate. Again, similarly, you'll see that you can carry a much larger current with a strong base. And in terms of the pH, you're looking at about a pH of 13 for a strong base, whereas a pH of around 8 will be seen with a weak base. So we've talked a lot about pHs. Let's quickly chat about it more. So the pH of 7, as I've already said, is neutral. pH of 14, which is one end of the pH scale, will be very strong alkali or base. A pH of 0 will be a very strong acid. And then you have the intermediate values, so pH 8 will be a weak alkali or base. A pH of 6 will be a weak acid. And let's look at the colours. So neutral is green. You get quite purpley at the very strong alkali end, and you get red at the acid end. And we like universal indicator because that can basically show you what pH you have. You add the universal indicator to the solution, it turns a certain colour which you can compare to a scale and work out the approximate pH. Going off on a bit of a tangent now, we're looking at soils, so that's where you grow your vegetables. Now, vegetables and crops grow best at a pH which is basically neutral, so close to 7. and crops really hate low pHs, so they don't grow well in acidic conditions. They can grow quite well in alkali conditions, so pH 8, and you often find that acidic soils will have an alkali such as calcium oxide that gets sprinkled on the soil to increase the pH.
We're now going to cover the salts topic, and when we're talking about salts we need to know a lot about acids and bases because that's where the salt originates from. So do remember your definition of an acid, which is that it is a H+ donor. A base is a H+ acceptor, and it also tends to be a hydroxide donor. And examples of bases include metal carbonates, metal hydroxides and metal oxides. Just remember the difference between a base and an alkali, they're very similar. An alkali is simply a soluble base, so remember all alkalis are bases, but not all bases are alkalis. So some background about salts. So effectively, a salt is formed when the hydrogen of an acid is replaced with either metal or ammonium. For example, say you had hydrochloric acid, you reacted it with potassium oxide, then you would end up with potassium chloride, which is the salt. Taking sulfuric acid now, pretend we reacted it with calcium carbonate, you'd end up with calcium sulfate, which is the salt. So now let's look at some common acids and the salts that they produce. Now in terms of the reactivity of acids, remember that only metals above hydrogen in the reactivity series will react with acids. So things like copper, silver and gold, which lie beneath hydrogen in the reactivity series, will not react. Elements at the very top of the reactivity series, such as potassium, sodium and lithium, they will react extremely explosively, and I don't recommend that anyone tries this because it would be extremely dangerous. So now let's take you through the salt equations. So we're going to start with looking at the general equation when you have metal plus an acid. That forms salt plus hydrogen, and I'm going to show you some examples. If you have metal oxide plus an acid, then you make salt and water. Metal hydroxide this time, it's the same as metal oxide in that you produce a salt and water. And lastly, metal carbonates, when you react those with acids, you produce a salt plus water, and then because of the carbonate, you produce carbon dioxide. So do make sure that whatever is on the product side started off on the reactant side. Don't start creating carbon dioxide on the right-hand side when there was no carbon on the left-hand side. And similarly, don't have hydrogen and water forming on the right-hand side. Only one of them forms, so make sure you know which one it is. So solubility rules, learning which salts are soluble and which are insoluble. The reason why I'm smiling is because this is disgusting. It's awful, I really struggle to remember them. Now there is a huge table which you can try and learn off by heart, but I much prefer to learn the rules, and if you assume that most things are soluble and learn the exceptions, that's a good way to go. So let's start by stating that all nitrates are soluble. All potassium, ammonium and sodium compounds are soluble. All sulfates are soluble. There are 3 exceptions, and that is lead 2, calcium and barium sulfate. All chlorides are soluble except from lead 2 chloride and silver chloride. Now we switch and we look at things which are insoluble. So we say that all carbonates are insoluble. The exceptions will clearly be the sodium, potassium and ammonium compounds, which makes sense because I've already told you that the sodium, ammonium and potassium compounds are soluble. And similarly, all hydroxides are insoluble, the exception being sodium, potassium and ammonium compounds. So let's just do a quick test on that. So I'm just going to say a couple of salts and you need to decide if they're insoluble or soluble. So starting with lead nitrate, that is soluble because it contains nitrates. Next up, potassium carbonate, that is also soluble because it contains potassium. Now we're looking at magnesium sulfate. That is soluble because remember all sulfates are soluble with a few exceptions. What about barium sulfate? Well, that was one of the exceptions you had to learn, so that is insoluble. And now calcium carbonate. That is insoluble because it is carbonate and it is not sodium, potassium or ammonium. So I hope you can see you can work it out using these rules. So let's look at the different methods for making these salts, and we're going to start by looking at soluble salts, but do notice these are ones which do not contain ammonium, potassium or sodium. So what you can do here is you can use metal oxide, a metal hydroxide or a metal carbonate. You react it with the acid and you form your soluble salt. You can also use metals plus acid, so it doesn't need to be combined with an oxide, hydroxide or carbonate, but do notice that you need a metal which isn't mega reactive, because clearly if you're reacting it with an acid you could end up with a dangerous explosion if you're using group 1 metals, so be sensible and use something like magnesium. Now the method you're going to actually use is crystallization. Your summary for this is that you're going to react, for example, your metal hydroxide with your acid. You're going to filter in order to remove any undissolved solid. Then you're going to evaporate, so you're going to place that solution in an evaporating basin over a Bunsen burner with gauze and a tripod, and you're going to get rid of excess water, so you'll evaporate some of the water. Then you're going to allow the mixture to cool, and eventually you want to let it dry out in a warm place, so on a warm windowsill, in a drying oven for example, or on paper. Looking at making soluble salts now, ones which do contain sodium, potassium or ammonia, you're going to use a slightly different method. Now the reason why you can't use the crystallization method I just described, because the sodium, potassium, ammonium are extremely soluble. So if you added them to acid, which contains water, they would react with both the acid and the water, and they would continuously dissolve away, meaning that there'd be nothing to filter and therefore nothing to evaporate. So that's why crystallization doesn't work in this case. So in this situation you have to use the titration method. So titration is the method you use when making ammonium, sodium or potassium salts. The reason you use the titration is because you need to know the exact volumes of acid and alkali you need to add in order to make the salt. So for example, we set up our burette and it contains the acid. We place the alkali in a conical flask together with an indicator, and then, as you know, with a titration you keep adding the contents of the burette to the conical flask, swirling all the time until you get that indicator to change. And when it does that, you know you have the exact volume of acid and alkali. Then you repeat the entire experiment, this time without the indicator, because obviously that would disrupt your salt. And because you know the exact volumes of both the acid and the alkali, you can create the exact amount of salt. There won't be any excess to dissolve away, and therefore you'll have a perfect salt. Once you've done that, your method is the same as we've just described with crystallization. Because you've got your solution, you now need to evaporate off the excess water. You need to allow it to cool, and then you're going to leave it to dry in a warm place again. So it's very similar to the crystallization method. You still use it, but unfortunately you have to use the titration method initially in order to obtain the correct volumes. Lastly, we're making insoluble salts. In this case, you're going to react 2 soluble salts, and obviously make sure you pick the right salts that will create the insoluble salt you're after. So if you're after barium sulfate as your insoluble salt, clearly the first thing you're reacting has to contain barium, so something like barium nitrate. The second thing has to contain sulfate, so it could, for example, be potassium sulfate. You react them together in order to form barium sulfate, and left over will be potassium nitrate. So do be sensible, make sure that whatever's going in will make your insoluble salt, which is why it's important that you know your solubility rules, so you know which salts are soluble and which ones are insoluble. By the way, this is a disgusting topic, everyone thinks so don't worry if you're finding it quite tricky. So when you're making insoluble salts, this is actually the most straightforward method you'll use. You're going to react, so you're going to mix those 2 soluble salts together. You're going to filter to remove any excess solid. You're going to wash, again to remove that excess solid. And lastly, leave to dry, and do state where you're drying it. Don't just say dry, so say in a warm place or on filter paper or in an oven. And this method we describe as being the precipitation method. I'm just going to describe an example of the precipitation method to try and show you exactly what is going on. So in this example, we're going to take silver nitrate and sodium chloride. Notice that they are both soluble because they contain nitrate and they contain sodium. So what happens when you place them in solution is all the ions separate, so you're left with Ag+, which is silver, chloride ions, which is Cl-, nitrate ions, which are NO3-, and sodium, which is Na+. Now, in order to make that insoluble salt, remember what we want to happen is for the silver and the chloride to be attracted, and indeed they are strongly attracted, forming silver chloride, which is an insoluble salt. Now the remaining ions, the nitrate and the sodium, are very weakly attracted, so they remain in solution, and they're the soluble salt formed. We can move away from that disgusting topic now and just look at generic tests. So the test for hydrogen, don't say it's the squeaky pop test, you won't get a mark for that. You need to say that you hold a lighted splint over the gas, and if hydrogen is present there should be a squeaky pop. With oxygen you need to say that it relights a glowing splint. Carbon dioxide, remember, turns lime water cloudy. Chlorine bleaches damp litmus paper, and ammonia turns damp red litmus paper blue. Now I've given you the most concise, precise definitions for this, so make sure you've learnt them. Every single word matters here. So for example, damp is worth a mark, red litmus paper worth a mark, so make sure you learn them properly. And now we're getting more complex and we're going to look at flame tests. So remember, if we have an unknown metal ion, a flame test is a good way of working out what that metal was. So in terms of carrying out a flame test, remember that you're going to use a clean nichrome wire, which is, you could clean it using hydrochloric acid, but the point is you don't want any contaminants on the end of that nichrome wire. Then you dip it in the sample to be tested, and then hold it in a roaring blue flame, and that is key. You can't be adding it to a yellow sooty flame, that won't work because the yellow will obstruct the colour, so hold it in a roaring blue flame. So the colours. Now if we've got lithium ions, you will see a lovely red crimson colour. Sodium, you'll see a yellow flame. And potassium, as with when you add it to cold water, you will see a lilac flame. Calcium goes an orange-red colour or a brick red colour, and copper goes a blue-green colour. If you don't want to carry out a flame test, you can use a precipitation reaction, and you can look at the colour precipitate formed once you've added sodium hydroxide. So if you add sodium hydroxide to something containing copper, you will see a blue precipitate formed. Iron 2 will form a green precipitate, and iron 3 will be a brown precipitate, and I remember those because they're kind of muddy, earthy colours, so it goes green for iron 2, brown for iron 3. Testing for ammonium ions now, which is NH4+, again add sodium hydroxide. You won't see a precipitate form in this case, instead a stinky gas will be released, which should be ammonia, and you test for the presence of that ammonia using the method I've already described, which is that it should turn damp red litmus paper blue. Okay, moving over now to test for negative ions. We've looked at metal ions and ammonium, so we're looking now at the halides, which is group 7, the halogens. So first of all, you need to add nitric acid. You add that dilute nitric acid in order to remove any carbonate ions which might interfere with your test. Following that, you add silver nitrate, and then you'll end up with a range of precipitates. So looking at the chlorides, if you add chloride ions to silver nitrate, you produce silver chloride, which is a white precipitate. If you add silver nitrate to something containing bromide ions, you make silver bromide, which is a cream precipitate. And lastly, adding silver nitrate to something containing iodide ions will produce a yellow precipitate. So notice those colours get darker. We go from white to cream to yellow. And be prepared to write the ionic equation for this, which will be, for example, with chlorine, it will be Ag plus Cl minus forms AgCl solid. Group 1 elements now, so remember that is the first column of the periodic table. It is the alkaline metals. They all have the same chemical properties because they have one electron in their outer shell. Now remember, as you descend that group, the elements become more reactive. They're all extremely reactive as it is, but as you descend the group, they get more reactive. The reason for this is because as you descend the group, the atoms get larger, because if you actually look at their atomic number, it's higher for potassium compared with lithium, so the atoms are larger. This means the outer shell electron is further from the nucleus, which means that it's more shielded by the inner shells of electrons. This means it's easier to lose the electron, and remember, when we lose the electron, that's when it partakes in chemical reactions, so it's more likely to do that, so it is more reactive than elements higher up than it in the periodic table. I've already touched on the fact that group 1 metals are extremely reactive. This means that they must be stored in oil because they'll react with the slightest bit of moisture. They're soft and you can actually cut them with a knife, and they oxidize very easily, so they go from being shiny to oxidized very quickly on exposure to air. Other properties they have is they have low melting and boiling points, which makes them quite unusual for metals, and they also have a low density, and we can see this when they're placed in water, they actually float on the water. So again, these are really quite unusual properties for the group 1 metals. Now they're very reactive, as I've already said, and they can react with oxygen to form oxides, so potassium oxide for example. They can react with cold water to form hydroxides, potassium hydroxide for example. They can react with the halogens. Remember, those are the elements in group 7 of the periodic table, to form something like potassium chloride, and they can partake in ionic bonding. Let's now look more closely at observations when they're added to water. So this will be true for all group 1 elements. First of all, they fizz, and what that actually means is they're releasing hydrogen gas. They float, they move around, they form a small ball which eventually dissolves. If you were to add universal indicator to that leftover solution, you would see that it would turn blue, and that makes sense because remember, blue indicates alkali and they're called the alkali metals, so that makes perfect sense. In terms of more specific observations, remember that lithium doesn't produce a flame. However, sodium produces an orange flame when added to water, and potassium produces a lovely lilac flame. Learn the word equations for when they're added to cold water. So I've already touched on this, but a group 1 metal plus cold water will produce a metal hydroxide plus hydrogen, which makes sense due to the fizzing that you witness. So taking lithium, for example, plus water forms lithium hydroxide and hydrogen. We don't add them to steam or to acid because that would be incredibly dangerous. They also burn in air and they produce very characteristic flame colours. So lithium burns to form a red flame, a crimson flame. Potassium again produces a lilac flame, and sodium produces a yellow flame. In terms of making predictions about group 1 metals below potassium, so things like francium. Now you don't need to learn these observations off by heart, but do notice that these observations with water will be more violent because obviously for all the reasons we've already described, the atoms are larger, more shells of electrons, the electron further from the nucleus. So just be prepared to talk about the fact that they'll be more violent, but you'd still see the same set of observations: fizzing, for example, a flame, moving around, floating, melting, etc. Right, so the halogens, we're looking at group 7, so these are the elements including fluorine, chlorine, bromine and iodine. Now don't forget their states at room temperature. Fluorine and chlorine are gases at room temperature. Fluorine is a yellow gas, chlorine is a green gas. Then you have bromine, which is a red-brown liquid, and finally iodine is a grey solid. Don't forget iodine undergoes a process called sublimation, which is when it turns directly from a solid to a gas, and in the case of iodine it goes from a grey solid to a purple vapour. Now the halogens react with hydrogen to form hydrogen halides. For example, hydrogen plus bromine forms hydrogen bromide. These are very acidic and poisonous, and they're also very soluble in water. So something like HCl gas will turn readily into hydrochloric acid, so that's HCl aqueous on addition with water. You need to know about halogen displacement reactions because more reactive halogens will displace less reactive halogens from their compounds. Let's quickly look at the reactivity of the halogens. So remember, at the top of the group, that's where they're most reactive. Towards the bottom, they're at their least reactive, and we can look at the reason for this. So iodine is much less reactive than fluorine because iodine is much larger, so it has far more shells of electrons. This means that the outer shell electrons are farther away from the nucleus, they're more shielded, and because of that it's harder to gain that extra electron in order to become full, hence they are less reactive, and this helps to explain why iodine is solid at room temperature. So if we look at the halogen displacement table, we tend to only look at the elements chlorine, bromine and iodine. You'll find that chlorine displaces both iodine and bromine from their compounds. You clearly don't react chlorine with itself, so potassium chloride, because there'll be no reaction. If you try and displace a potassium chloride, for example, using iodine, that won't happen because iodine is less reactive. So just learn the rules for this and the summary equations. In terms of their general properties, remember they have low boiling points and low melting points, and they are poor conductors of heat and electricity. the reactivity series. So you need to learn the order of metals in the reactivity series, and that is potassium, sodium, lithium, calcium, magnesium, aluminium. Then we mention carbon because although it isn't a metal, it's good to use it as a reference point. This is followed by zinc and then iron. Hydrogen comes next, not a metal, but still a good reference point. And lastly, our unreactive metals go copper, silver, and then lastly, the most unreactive is gold. And that explains why you find silver and gold native in the Earth's crust. You can literally just find it in streams and rivers, and that's because it's incredibly unreactive. Even though aluminium looks fairly reactive because it appears quite high in the reactivity series, due to its oxide layer, it means it's less reactive than you would imagine. So we have an unknown metal and we don't know how reactive it is. So there are several things we can do to try and determine its position in the reactivity series. So first of all, we would try to react it with cold water. Now only very reactive metals, such as those found in group 1, so we're looking at potassium, sodium and lithium for example, will react with cold water and they'll form metal hydroxide plus hydrogen, which we've already met. If they don't react with cold water, you can then try steam, and this will produce a metal oxide and hydrogen. And then lastly, if it doesn't react with steam, you can try acid, and that will produce a salt plus hydrogen. And you obviously wouldn't try reacting group 1 metals with acids because they are far too reactive. Do notice that when you look at the reactivity series, only elements which are more reactive than hydrogen will react with acids, and that's because acids contain hydrogen, such as hydrochloric acid, it's HCl, sulfuric acid, H2SO4, nitric acid, HNO3. So in order to react with acids, they must be more reactive than hydrogen.
We have to look at a pretty boring part of the specification, which is all to do with the effect of heat on different types of metal hydroxides, carbonates and nitrates. So first of all, if we add heat to metal hydroxides, what do you find? Well, you find that hydroxide decomposes which means it breaks apart under the influence of heat. The exception to this is sodium and potassium hydroxides, which do not decompose, and your product produced is oxides and water. If you have a metal carbonate now, you find a similar sort of situation, which is that the carbonate decomposes the exception again being sodium and potassium. But this time, as your products, you're going to produce oxides and, as the name should hopefully suggest, carbon dioxide. Looking at the effect of heat on metal nitrates, they all decompose. Again, the exception here is sodium and potassium. The metal nitrates which do decompose produce oxides, nitrogen dioxide and oxygen. Nitrates and sodium and potassium produce different products, and these are nitrites and oxygen. So it's not difficult, but it's an annoying thing you'll just have to learn. Now, we know that metals are incredibly useful. They're used as all sorts of building materials in everyday life, such as aluminium drinks cans, but we need to know how we can extract them. And there are two main methods, which is either heating with carbon or electrolysis. And the method you use very much depends on the reactivity of the metal, because you can only use the heating with carbon method if your metal is less reactive than carbon. For metals which are more reactive than carbon, heating with carbon will have no effect, and therefore you have to use electrolysis, which is far from ideal because electrolysis is an incredibly expensive process as it involves the use of electricity. For extremely unreactive metals, such as gold and silver, you find these native, so not reacted with oxygen or anything. They're not found as oxides, they're literally found as gold and silver, native in the Earth's crust, which is why people used to pan for gold in rivers in America about 100 years ago in order to find the gold sitting in the riverbed. So let's look at the blast furnace, which is all to do with purifying iron. And that iron exists as iron oxide in the Earth's crust, which we call hematite. Remember that heme means related to iron in the way that hemoglobin, found in red blood cells, contains iron. So try to remember that. Now, we're going to use the heating with carbon method. And the reason we can do this is because carbon is more reactive than iron. So this is a good process because it's not incredibly expensive. So let's start by looking at the raw materials which will enter our blast furnace. These are obviously the carbon, which is entering in the form of coke, the iron oxide, and it's iron 3 oxide, and lastly limestone is added to remove acidic impurities. And now it's essential that we look at the various equations involved in the blast furnace. So our first step is reacting carbon, so the coke, with oxygen to form carbon dioxide. And if they ask you, the point of this reaction is to produce the heat needed. Next step, we're going to react that carbon dioxide produced in that step with carbon to produce carbon monoxide, and do make sure you balance the equation. And remember, this is going to be the reducing agent, which is all important as that actually is going to remove the oxygen from the iron oxide. The next important step is what we're really after, which is purifying that iron. And it's going to produce iron by itself and carbon dioxide. Let's do some balancing. And our summary here is that iron oxide is reduced to iron. Now it's important that we look at the limestone step. So this is kind of separate to everything that's gone on before. So we have our calcium carbonate, which is obviously limestone. It's going to undergo a thermal decomposition reaction, so make sure you can name the type of reaction, to produce calcium oxide and carbon dioxide. And it's that calcium oxide that's important because it reacts with the acidic impurities found within the blast furnace, producing calcium silicate, which we remember the formula of, because remember most people have a calculator which is of the brand Casio. And if you remember that it's Casio 3 and making sure that you lower and uppercase the appropriate letters, you can therefore remember calcium silicate's formula, and its colloquial name is slag, which is a very strange name, but that floats on top of the iron. And that is a summary of the blast furnace. Remember, this final reaction here is a neutralization reaction. Let's now look at how iron is converted to steel, and remember that steel is an alloy of iron, and that's because it contains a mixture of both iron and carbon. Now, as we've already discussed, molten iron is produced by the blast furnace, and then at this point more oxygen is added, and that's to help remove impurities which include carbon, sulfur and phosphorus impurities within the iron. And what you find is waste gases of carbon dioxide and sulfur dioxide are produced, and phosphorus oxide, which is the final impurity, is removed as a solid. And then at this point, similarly to the blast furnace, we add calcium oxide, which has obviously come from the thermal decomposition of calcium carbonate, and this reacts with the silicon dioxide and phosphorus oxide impurities to produce slag. So it's very similar to what we were just talking about, just in slightly more detail, and remember that that floats on top of the molten iron. And then carbon is added in very specific percentages to make either low carbon steel or high carbon steel, dependent on the properties of the end metal. So another very important metal now, which is zinc, and we get zinc out of the ground mainly as a compound which is zinc sulfide, and we have to roast this in air, which causes it to react with oxygen to form zinc oxide and sulfur dioxide. And then with that zinc oxide, it's very similar to the blast furnace, so we need to reduce it using carbon monoxide to give zinc plus carbon dioxide. And then at this point, to purify, we can either use electrolysis or we can separate the mixture using fractional distillation, so similar to the organic chemistry method. So we need to now quickly look at recycling metals, because the problem with aluminium, as we know, it's incredibly expensive to produce due to the high energy costs. So there's big advantages related to recycling. However, because there are so many different alloys, i.e. different versions of that aluminium, it's incredibly difficult to separate and recycle. Iron and steel, however, is more straightforward to recycle.
When you now look at aluminium, because that's another useful metal, that's also too reactive to be found by itself in the Earth's crust, so it's found combined with oxygen. You can't use the blast furnace in order to obtain the aluminium, because aluminium is more reactive than carbon. So if you try and burn them together, nothing happens. So this is where electrolysis comes in, and we use aluminium oxide, we electrolyse it, and we have to therefore use huge amounts of electricity, and that's why it's a far more expensive process compared with iron's blast furnace. The second real expense with aluminium is, if we look more closely at the reaction taking place, what you find is there are carbon anodes which dip into the solution containing aluminium oxide. Because they're anodes, clearly they will be positively charged. This means that they attract the oxygen, which is the negative ion. And if we look at the summary equation, we can see that O2-, which is the oxygen ion, loses electrons, so it's oxidized to become oxygen gas. But the oxygen gas formed actually reacts with the carbon electrodes, forming carbon dioxide, which actually burns away the electrode. So in a month or so's time, the whole electrode disappears effectively, so it needs replacing really regularly, which is why it's such an expensive process. We might as well talk about the reaction occurring at the cathode. So remember, that is the negative electrode. So here the aluminium ion will be discharged. So aluminium, Al3+, it will be reduced because it has to gain electrons in order to become Al. So it gains 3 electrons, which is why we say reduction has taken place. And have another look at the electrolysis part of this video if you're unclear as to what I'm saying. Why do we go to such effort to obtain aluminium? Well, it's because it's an extremely useful metal. It has really great properties, mainly because it has low density. So compared with other metals, it's light, but we can't say light in the exam. We say low density, which means it's good for use in making aeroplanes. We've obviously also seen its use in making drinks, cans, etc. It's also a really good conductor of heat, which is why you find a lot of pans are made out of aluminium, which is why wiring can sometimes be made out of aluminium. Looking at the uses of iron, and you need to know about the different types of iron in terms of how much carbon they contain. Don't forget that when iron has carbon combined with it, it's now formed an alloy, and that alloy is called steel. So looking at low carbon steel, so that's steel containing less than 0.25% carbon, you find that this steel is very strong, malleable and ductile. Don't forget, malleable means it can be hammered into shape, ductile means it can be drawn into a wire. And its use is in car bodies, so that's to make the outside of a car, for making bridges and shipbuilding. There are disadvantages with using low carbon steel, and that's because it rusts easily and it's very heavy due to its high density. Stainless steel, this is an alloy containing also chromium, nickel, and obviously iron. This is highly resistant to corrosion or rusting, which means it makes great cutlery. So a lot of your cutlery, your knives and forks and spoons will be made out of stainless steel, and you'll probably see it written on there. It's also used to make saucepans and gardening tools.
Now copper. Copper is commonly used in electrical wiring, and that's because it's an excellent conductor of electricity. Coupled with that is its ability to conduct heat, which means it can be used to produce cooking pots and pans, so saucepans. Now zinc. Zinc is often used to coat metals, and when zinc is used to coat metals such as iron, we call this galvanizing. And remember, this is all to do with making something like iron less susceptible to rusting. So if you cover it in zinc, because zinc is more reactive than iron, it corrodes instead of iron. Thus protecting the iron object. And we call this sort of protection sacrificial protection. And places you find galvanizing is things like zinc buckets, the side of ships. You'll see zinc blocks. Zinc is also good for making alloys such as brass. So brass is an alloy containing copper and zinc. It's hard and shiny and is used in electrical plugs as the pins, so the bits that stick out of the plug, and that is a Tauber drawing. It's also used in door locks, keys and musical instruments, so like a trumpet will be made out of brass. I know we keep talking about iron, but remember to just point out the fact that iron's properties can be changed by combining it with differing amounts of carbon to make different types of steel, or adding things like chromium and nickel to produce stainless steel.
Now we need to look at the chemical and physical tests for water. So the physical test for water is you just need to check a substance's boiling point. If it boils at 100 degrees Celsius, you know you have water. And linked with this, how do you show that water is pure? Well, I've already talked about pure substances having one distinct boiling point, and the same is the case with pure water. The whole lot should boil at 100 degrees. If it's boiling over a range, it tells you it's not pure. Now, using a chemical test for water, you want to add white anhydrous copper sulfate. Anhydrous means lacking in water. Once it's exposed to water, it should turn blue, and that tells you that the substance you have is water.
How do we make potable water or water suitable for drinking? So first of all, we want to find a clean source of water. So ideally not one that's full of pathogens, so bacteria and dirt. And then after this, we do need to make sure we clean it a little bit. So we use a screen to trap any large particles. A coagulant is added, and a coagulant is a substance which causes particles to stick together. Next up, flotation tanks. Make these particles float so they can be removed. They're literally skimmed off the top. Then we filter to remove smaller particles. Add chlorine, because chlorine, remember, it's a halogen, it's incredibly toxic, so that helps to kill the pathogens. But obviously we don't want to add too much chlorine because then it would be unsafe for us to drink. And then lastly, that water needs to be stored in a clean environment. Strange part of the specification now, but what is that water used for? Well, obviously it's used within the home for cooking, washing our clothes, washing our bodies, and we need to drink it. We find water in farms for both the animals to drink and we need to water our crops to ensure that they grow. Water is found in power stations, because remember, a fossil fuel power station works by burning the fuel, so it heats water, so that's where the water comes in, to produce steam, which turns the turbine, which turns the generator, which produces electricity. And then just generally within industry, for washing chemicals, cooling tanks, and a general solvent that you can dissolve a solute in. Linked with the use of water as an essential part of the human diet, so it needs drinking, what are the consequences of an inadequate or dirty water supply? Well, you get infections, and if you're really unlucky, you could get something as bad as cholera and typhoid, which are both life-threatening diseases. More typically, you'll get diarrhea. And then linked with this is poverty. If you don't have enough water, then you won't be able to grow crops, and that can lead to starvation. So water is absolutely essential, as is a very clean supply of water.
Moving on to the components of gas in air. So let's look at air. What does it consist of? Well, it's 21% oxygen, 78% nitrogen, 0.9% argon, 0.04% carbon dioxide, and everything else is other noble gases.
So how can we separate oxygen and nitrogen from liquid air? Well, first of all, we're going to remove the carbon dioxide and water vapour, and then we're going to use fractional distillation, which, remember, is a method used to separate liquids of different boiling points, and you find that oxygen and nitrogen have different boiling points, so they can distill at different temperatures.
So complete combustion is when you burn something in a plentiful supply of oxygen, and that means you produce carbon dioxide and water as a byproduct, which is a good thing because neither of these things are toxic, although there are obvious environmental issues with carbon dioxide production due to it being a greenhouse gas. Incomplete combustion is when you have insufficient oxygen, and that means you don't produce carbon dioxide. This time you produce carbon monoxide and water. So what are the issues relating to carbon monoxide? Well, it is extremely toxic and poisonous, and that's because it combines with the hemoglobin in red blood cells, forming carboxyhemoglobin, and that means that red blood cells can no longer transport oxygen around the body. Acid rain now, so we're looking at more environmental issues. So acid rain comes from two areas. Firstly, nitrogen and oxygen in car engines reacts due to the high temperatures found, forming nitrogen oxide. That reacts with water in the atmosphere, forming nitric acid. So there's your first acid rain. Next, crude oil can contain sulfur impurities, and when burnt they form sulfur oxides. That reacts with water, forming sulfuric acid. So there's your second acid rain. And acid rain gets into lakes and rivers, making them too acidic, therefore killing aquatic animals. It damages trees and it damages limestone buildings, and you must mention that they're limestone. But we now need to look at the effect of excess carbon dioxide on the environment. So remember, carbon dioxide is a greenhouse gas. So enhanced greenhouse gases, so more CO2 being released, will lead to global warming. Now, global warming causes polar ice caps to melt. Because they've melted, it means that there is a rise in sea level, which floods low-lying land. This obviously causes the destruction of many habitats. It can cause the extinction of species that get caught up in it. And other effects include changes in bird migration patterns, so that's where they fly in the summer and the winter, and also increased extreme weather. Looking at protecting iron from rusting. So rusting is when metals flake away, and you only use the word rust when you're talking about iron. If you talk about any other metal, you can't call it rust, you have to say it corrodes. So you could say that zinc corrodes, but only iron rusts. So what conditions are needed for rusting to occur? You need water and oxygen for this, and salt actually increases the rusting process but is not necessary. What are the different ways in which we can prevent rusting? There are the simplest ways, which is just simply painting or using oil and grease to protect the iron and stop it being exposed to water and oxygen, or you can become more fancy and use methods such as galvanizing. So galvanizing is when you use a more reactive metal such as zinc, and it reacts before the iron. And so actually what happens is the zinc ions and donates electrons, and what that means is the electrons can flow to iron, and therefore if the iron starts to rust and form ions, this is hard, why have they got the same name? Those electrons which have been donated from zinc can help the iron form its iron atoms again so it doesn't rust away. Try not to worry too much if you're not understanding what I'm saying. Just learn that galvanizing is using a more reactive metal to protect iron. When other metals oxidize and react in preference to the iron through the method of galvanizing, don't forget we call this sacrificial protection.
Let's look at fertilisers now. So remember, we add these to our fields to help the crops grow a little better. So what elements do fertilisers contain? Well, firstly, they contain lots and lots of nitrogen. And nitrogen is essential because it is needed by plants to produce amino acids and proteins. Fertilisers also tend to contain a lot of phosphorus, which is needed in the healthy growing of roots and to help crops ripen. And then lastly, potassium. Now notice that lots of fertilisers are called NPK fertilisers, and we can see that the N stands for nitrogen, P stands for phosphorus, and K stands for potassium as per their symbols in the periodic table. We're going back to potassium. Why is this needed by plants? Because they use it to produce proteins and to help them resist diseases. So, chemistry involving the element sulfur, or sulfur as it's spelled more commonly now with the F. So let's of all start by listing some sources of sulfur. So that includes volcano rims. So at the top of volcanoes you can find lots of sulfur. There are underground beds, so large areas underground which contain sulfur, and these are found in the following countries: Mexico, Poland, and the USA. It can also be found inside metal ores, and its name is galena. And lastly, you get sulfur as sulfur impurities found within fossil fuels. And remember, this is a major issue when you burn the fossil fuel. The sulfur impurities react with air, with oxygen, forming sulfur dioxide, which we know can contribute to acid rain. However, there are lots and lots of uses of sulfur, and you need to be able to list them. So first of all, it's used to make sulfuric acid, which you need to know is H2SO4. It's also used to toughen the material rubber, and we call that process vulcanizing. You find that many of your makeup, so your cosmetics, your drugs, pesticides, shampoos, lotions, etc., dyes, all contain sulfur. Sulfur is also added to cement to make sulfur concrete, which has some very useful properties, including the fact that it's resistant to acid, which is good because with increasing problems with acid rain, you don't want concrete which effectively dissolves away in the acid rain. Sulfur is also used to bleach wood pulp, which is later used to make paper. And lastly, it's used as a preservative. So if you've ever eaten things like preserved apricots, they have this very bright orangey yellow colour, and that's due to the presence of sulfur, which actually kills bacteria. So as you look down this list, you can see that sulfur has some incredibly widespread uses and is indeed one of the most useful elements found on the earth. It now makes sense for us to look closely at how sulfuric acid is made, and this is made in a process called the contact process. So first of all, you need to take sulfur and you react it with oxygen to form sulfur dioxide, which is a gas. And then we need to get that sulfur dioxide and convert it to sulfur trioxide in a reversible reaction where it reacts with oxygen. Because this is a reversible reaction, we need a catalyst, which is vanadium 5 oxide, and an optimum temperature of approximately 450 degrees Celsius. This is an exothermic reaction, by the way. At this point we have our sulfur trioxide, and we can't just convert it to sulfuric acid by adding water because it creates a horrible fog. So instead, weirdly, you have to get that sulfur trioxide and react it with pre-existing sulfuric acid, so that's H2SO form, to form H2S2O7, which we call oleum, or fuming sulfuric acid. And then we take that oleum, H2S2O7, we add water to it, and then we can produce plenty of sulfuric acid. So listing some uses of sulfuric acid, well, that includes the fact that it's found within car batteries, fertilisers, paints, pigments and dyes, plastics, and soaps and detergents.
Moving on to thermal decomposition now. So what does that actually mean? Well, thermal means to do with heat. Decomposition means breaking down. So it's breaking down a substance using heat. And this is what happens when metal carbonates are heated, they break down. For example, copper carbonate, when heated, it goes from being a green solid, which is copper carbonate, it's broken down to copper oxide, and copper oxide is a black solid. All the carbonates respond quite similarly, so if we had calcium carbonate now, we heated it, it would break down to calcium oxide and carbon dioxide.
So looking more closely at carbonates, and specifically calcium carbonate, which we know is limestone, which is really the limestone cycle. So what we need to do first of all is get our calcium carbonate, we heat it, and it thermally decomposes into calcium oxide and carbon dioxide. So as I just said, that is a thermal decomposition reaction. If you add water to calcium oxide, you get calcium hydroxide, and both calcium hydroxide and calcium oxide are both very useful products. Remember that they're both alkali, so therefore they can be used to neutralize acidity in both lakes and soils, so very useful for farmers. And they can also be used to remove sulfur from waste gases in power stations. Now the original substance, calcium carbonate, that's also incredibly useful because, as I've already said, it's added to the blast furnace to help remove acidic impurities, and it actually produces slag, and it can actually be mixed and heated with clay to produce cement, so an incredibly useful building material.
So let's look at organic chemistry, one of my favourite topics. So first of all, organic chemistry, what are we talking about? We're talking about hydrocarbons. So what is a hydrocarbon? It's a compound containing hydrogen and carbon only. Make sure you say only in order to get that second mark. So when we're looking at organic chemistry, we're really looking at different families of compounds, and the simplest family is the alkanes. And I'm going to show you now how to draw out the first 4 alkanes, and we'll have a look at their general formula.
Let's look at how we're going to draw various families of compounds, starting with the simplest, which is the alkane family. Do notice their general formula is CnH2n plus 2, and you must obey that when you're working out the molecular formula. If we take C4H10 as an example, this is a molecular formula because it shows the actual atoms of each element present in the compound. So it shows that this particular compound has 4 carbon atoms and 10 hydrogens. To make it into an empirical formula, just cancel down those numbers. So it becomes C2H5, because you can obviously divide 4 and 10 both by 2. This is therefore the empirical formula because it shows the actual atoms of each element present in a compound. And then just to notice, a displayed formula is when you draw out all the bonds, so something like that. So let's start by working out the first alkane. So obviously it's going to have 1 carbon atom. According to the general formula CnH2n plus 2, so substitute in the number of carbon atoms as n, so it becomes C1, and then 2 times 1 is 2, plus 2 is 4, so H4, Because it looks a bit strange to write the 1, I'm just going to erase that. There's an invisible one. So it's CH4. Its displayed formula looks like this, which is you draw the carbon in the middle and hydrogens around the outside, remembering that each carbon atom forms 4 bonds, each hydrogen forms 1 bond, and you must remember that to help you draw them. Its name, well, it contains 1 carbon, which is why it's meth, and it's an alkane, which is why it's methane. So looking at the second one this time, 2 carbons, so we're going to have C2, and then according to the general formula, 2 times 2 is 4, plus 2 is 6, so its molecular formula is C2H6. Drawing it out, therefore, carbons in the middle, then you've got your hydrogens filling up around the edge, each having 1 bond, and each carbon atom has 4. Because it's still an alkane, it ends in ane, but it contains 2 carbons, which is why it's ethane. The third one now, so it's C3, 2 times 3 is 6, plus 2 is 8, H8, 3 carbons in a line, ends in ane, it contains 3 carbons, so it's propane. For 4 carbons I ran out of space, so it will be C4H10, and it contains 4 carbons, which is why it's bute, still an alkane, so butane.
So these are the simplest hydrocarbons, and we call them saturated, and that's because all the carbon bonds are single. If we look at alkenes, they are unsaturated, and that means they contain a double carbon bond. I'm going to show you how to draw the first 4 alkenes.
Let's now look at the alkenes, and remember they have a general formula, which is CnH2n. Let's first of all start by discussing the functional group of the alkenes. Remember, this is the series of atoms or bonds which makes a particular family of compounds special. So here we see that the alkenes contain a C double bond C. By definition, therefore, they need a minimum of 2 carbon atoms to exist, which is why one carbon alkene does not exist. And we have to start with the 2 carbon. So starting with the 2 carbon one, we know we need to substitute 2 in as the end, so it becomes C2 and then simply H4. The displayed formula, we need a double bond, and therefore we're going to fill up our hydrogens. Do notice again that the carbons have 4 bonds, the hydrogen has 1, contains 2 carbon atoms, which is why it begins with eth. It's an alkene, so it's ethene. Looking at 3 carbon atoms now, so C3H6. Again, make sure you're filling these up properly, double checking the bonds. I can't reiterate this enough. And this will be 3 carbons, so prop, it's an alkene, so propene. Now looking at the 4 carbons, which is when it gets a bit more interesting. So we've got C4H8, and therefore we can draw the first version of this like this. In terms of its name, it's butene. However, we now need to look at the other available isomer. Remember then, isomer is something with the same molecular formula but different structural formula. So if we draw that molecular formula out again, C4H8, but we try and work out a different structural formula, we can simply shift that double bond along so it now appears in the middle, and now just fill in those hydrogens, making sure you don't draw too many bonds on those central carbons. And you can see this is still C4H8, however the structures are different, and therefore these are both isomers, and the way in which we name them is according to where you find that double bond. Because the double bond in the black version is between the first and second carbon, we call it butanene. Because the double bond is between the second and third carbon atom, we call this butene.
Now, these families of compounds we call homologous series, and that's just a fancy way of describing a family of compounds. So what can we say that all members of the same homologous series have in common? So what do all alkanes have in common? What do all alkenes have in common? Well, first of all, they have the same chemical properties, which makes sense. They're going to react in a similar way because they have the same functional group. They're therefore going to have the same functional group, which is good because I just said that. They obey the same general formula. So all alkanes, for example, will follow CnH2n plus 2. Whereas all alkenes will obey CnH2n. And then they show a trend or a gradual change in physical properties, which again makes sense. So ethane has 2 carbon atoms, whereas methane has 1. So therefore you'd expect ethane to have a higher melting point and boiling point, which it does. So what is a functional group? Well, it is an atom or a group of atoms which determine the chemical properties of a compound. So we talked about alkanes and alkenes, but where do they all come from? And they come from crude oil, which is a black sticky substance which comes out of the Earth's crust, and it has made some people billionaires because this stuff is worth a lot. Why? Because once it has been sorted, once it has gone through fractional distillation and been separated out into various fuels, that can be sold for a huge amount of money. Why? Because fuels are essential for how we run our lives, it's how we heat our homes and how we run our cars. So what is a fuel? Well, it's a substance which releases energy when burnt. We've talked about crude oil, but how is fractional distillation actually carried out? So we get our crude oil, which we know is a mixture of hydrocarbons, we heat it until it evaporates, and then we pass that vapour into a fractionating column or tower. Now that fractionating column has a temperature gradient, which means it's hotter at the bottom and cooler at the top. So in terms of these various crude oil fractions, and a fraction is just a group of compounds with similar boiling points, they will condense at different positions within the fractionating tower. So the longer chains will condense at the bottom where it is hottest.
So looking at fractional distillation, so we're looking within the fractionating column and we need to know the different fractions starting from the top and various uses. So refinery gases, this is bottled gas used in central heating and cooking, so within our homes basically. The next fraction down we have petrol, otherwise known as gasoline, and as the name suggests, it's used as fuel for cars. Getting slightly longer in terms of our carbon chain, we have naphtha. Its main use is to produce chemicals. Then we have paraffin, which is used as jet fuel. Diesel oil now. This is a heavier fuel and it tends to be used in lorries and buses. Getting longer again with our carbon chain, we have fuel oil, which is fuel for ships. And we also produce lubricants, which are slippery and therefore used in waxes and polishes. And then the last fraction is bitumen. It's black and sticky and we can use it in road surfacing.
A couple of words to be aware of. First of all, viscosity. So that's how readily a fluid flows. Be aware that the more viscous a fluid is, the less readily it flows. So honey is very viscous because it's slow to flow. I like the fact that that rhymed. And water is very unviscous or not viscous at all because it runs very quickly. Flammability, obviously that's to do with how readily something sets alight. Volatility is how readily something turns into a gas. So if we take the various fractions and we make a few comparisons, let's compare the viscosity, volatility and boiling points of bitumen compared with refinery gases. So clearly bitumen will be more viscous, it will be less volatile and it will have a higher boiling point. It will also have a darker colour because it's a brownish sticky colour, whereas refinery gases are colourless. So do be aware and do be willing to make comparisons and make full comparisons. So say refinery gases are lighter in colour, have a lower boiling point, are less viscous, etc. Cracking now, remember that is a process carried out in order to break large hydrocarbon chains into smaller, more useful ones, and it's all due to demand because effectively the shorter chain hydrocarbons, the shorter chain alkanes and alkenes make much better fuels than the long chains, which is why we carry out cracking. Do remember that you need a high temperature, which is between 600 and 700 degrees Celsius, and you need an alumina or silica catalyst in order to speed up the process. Let's touch on a few reactions that you need to be aware of.
I could ask you what is the test for an alkene or an unsaturated hydrocarbon? That's actually the same question. So effectively you're testing for the presence of the C double bond C. What you'd write as your answer is that you add bromine water, and in terms of your observations, what you would see is that it would go from orange to colourless. Let's actually look at an example. So we'll take ethene. We're adding bromine water. Remember, bromine is diatomic, hence why I'm saying Br2. And then what happens is the double bond breaks, meaning that there are two available spaces for bromine to join on, which is here and here. And there's no byproduct because of that. And because bromine simply added itself, you say that this is an addition reaction. So what is the type of reaction? Addition, you add bromine water and it turns from orange to colourless. Now looking at alkanes reactions with bromine water. So alkanes, or a saturated compound, it's basically the same thing. What you see this time, I'm going to take methane as my example, but I could have used ethane or propane. We add it to bromine water. But what happens this time is one of the hydrogen pops off, the bromine joins, you complete the rest of the molecule, and what you have left over is clearly a hydrogen that's just left methane and another bromine atom, which is why this is your equation here. Because all that's happened is that hydrogen has simply been swapped or substituted for bromine, we say that this is a substitution reaction. So you can actually see what's happened here. Looking at the alcohols now, notice that their functional group is OH, and do remember that each oxygen atom can form 2 bonds, while hydrogen obviously forms only 1, so we'll bear that in mind now. So starting with the most simple version, which contains 1 carbon, its name, 1 carbon, so meth, is an alcohol, so it's methanol. In terms of drawing it, draw your functional group coming off first. I've already told you it forms 2 bonds when you're talking about oxygen, and then just fill up with hydrogens. And that is methanol. 2 carbons now, so 2 meaning it's eth, so ethanol. This is the alcohol found in natural alcoholic drinks. So we need 2 carbons. Here's our functional group, the OH. Filling up with hydrogens, there's ethanol, 3 carbons, so prop, alcohol, propanol. Do notice there is a second isomer of propanol, because actually what I've drawn here is propan-1-ol, but there's also propan-2-ol, so we can actually move the position of that alcohol functional group to be on the second carbon here, and then just fill up with hydrogens. Try and draw your hydrogens better than I am, these don't even look like H's.
So how can alcohols be oxidized? Firstly, you can burn them in air, which we would call combustion, because that's burning. Secondly, they just react naturally with the oxygen in air, and that's due to the action of microbes in the air. We call that microbial oxidation. And lastly, you can heat them with potassium dichromate in the presence of dilute sulfuric acid, and that will also oxidize them. So if we're taking ethanol, for example, it will be oxidized to ethanoic acid. So we've taken an alcohol, we've oxidized it, and it has produced a carboxylic acid. Some uses of alcohol, aside from use in alcoholic drinks, they can also be used as good fuels and in perfumes, and sometimes you'll see on your perfume bottle it might say alcohol free, because many actual perfumes do contain alcohol. Looking at now at the production of alcohol, we need to know the 2 main ways, which is fermentation and hydration of ethene. So we need to compare both of these methods for making alcohol. So let's first of all look at their raw materials. Hydration of ethene is obviously ethene, so that's going to be from crude oil, which means it's a non-renewable resource, whereas fermentation involves using sugarcane and using your old-fashioned approach, so using yeast in order to ferment that sugarcane to produce the ethanol. So obviously that uses a renewable resource. In terms of temperature and pressure needed, fermentation, that's going to use low temperatures and pressures, whereas hydration of ethene is a very industrial process, so it involves high temperatures and pressures. The type of process involved now, we say that fermentation is a batch process, and that's because you mix together all the reactants and you leave it for several weeks or months. You remove the alcohol and then you start again, hence why it's a batch process. whereas hydration of ethene is a continuous process because it can just carry on endlessly. As long as you've got the reactants and the reaction conditions, it keeps going. Let's look at our reaction equations now. You've got glucose from the sugarcane, so C6H12O6, and it breaks down using anaerobic respiration by yeast into ethanol plus carbon dioxide, and we know carbon dioxide can be used in bread making. Hydration of ethene is, as the name suggests, adding water to ethene. So you've got C2H4, you add H2O to it, and that's how you produce your ethanol. Lastly, look at the product produced. Fermentation obviously makes a pretty impure product because it's got lots of other things mixed in with it, whereas hydration of ethene makes a pure product. So be aware when they give you an exam question and they give you a situation and they tell you what sort of resources are available, whether there's lots of electricity available, that sort of thing, be aware of which method would be better to use.
Right, let's look at the carboxylic acids now. They have a more complicated functional group, which is COOH. Do notice in the top right corner that this actually looks like a C with a double bond to the O, and then a sort of alcohol group coming off the bottom of it. So 1 carbon, because it is a carboxylic acid, we're going to start with meth because it's 1 carbon, but it's methanoic acid. In terms of drawing it, draw that carbon, draw the functional group, and now just count up and make sure you've got enough bonds coming off the carbon. So far it has 3, we know it needs 4, which is why it just needs a single H here. Looking at 2 carbons now, so that means it's F, so it's ethanoic acid. 2 carbons next to each other, here's our key functional group. Fill up with hydrogens where necessary, and that is ethanoic acid. Looking at the 3 carbon version, so propanoic acid, 3 carbons in a line, there's your functional group, fill up with H's. Right, esters. So let's look at their general equation for their formation. So we need to react a carboxylic acid with an alcohol. This is a reversible reaction and it produces the ester plus water. The functional group of the ester looks like this, by the way. I'm going to show you an example now. So a carboxylic acid, I'm going to pick methanoic acid. I've decided to react that with ethanol. Now, in terms of naming it, notice that the first part of the ester's name comes from the alcohol, which is why it begins with ethyl. The second bit comes from the carboxylic acid. Esters always end in an OH, so it's ethyl methanoate. And we've got water being formed. Let's draw it all out now. So, here is our functional group of the carboxylic acid. Fill up the hydrogens. We're adding it to ethanol, which is fairly straightforward to draw. We know we're losing the water. That water is going to come from here, and then it's a matter of sticking together the remaining molecules. There's me drawing the remaining water, and this here is ethyl methanoate. Remember, you need a strong acid, sulfuric acid catalyst here. The reason we're interested in esters is they have lots of useful properties, such as the fact that they are very volatile, and that means they have widespread uses in perfumes because they evaporate easily. They can also be used in food flavourings. Now we're going to look at addition polymerisation, and they could ask you to show this as an equation. So I'm going to show you what's going to happen. We are taking a monomer, such as ethene. Got to make sure I pronounce that properly, ethene. This is your monomer, which means it is a small subunit. Because it is an addition reaction, we're effectively going to add lots of them together, which is why we write an N here. That just means you have lots of them. Then we need to draw some big square brackets. You want to break that double bond, as I've done there, extend the bonds, and now just complete the rest of the structure. And you write an N here to show that there's lots of them, and this is the polymer formed. And if you were to name them, we know that that was ethene. Because there's many of them joining together, we say that the polymer formed is polyethene, which you've probably heard of before and not realised it's polythene. and that's used to make cling film and plastic bags, etc. Let's take propene now, and I'm going to draw propene like this just to make it easier to draw the polymer. But I hope you can see that that is propene, it is C3H6. Again, that's our monomer. We're going to have any number of them, hence the N, big square brackets, break that double bond, and now just complete the atom. Be very careful where you draw your bonds, make sure those carbons are joining. Extend the bonds out, draw your N, and this is therefore polypropene. This is a harder plastic than polyethylene, so it's used to make buckets, windows, etc. Let's take a third example now. Again, square brackets, break that double bond, extend the bonds, and then just complete. And this is polytetrafluorine.
What does biodegradable mean? It means breaking down a substance using microorganisms. And everything these days, we want it to be biodegradable. We don't want plastics hanging around for hundreds of years, which is why it's really good if they say that they're biodegradable. What problems are associated with the disposal of addition polymers, so really problems associated with plastics? That is that most of them are non-biodegradable. They are unreactive, which means it's difficult to break them down. And when you burn them, as a different way of disposing of them, they produce lots of toxic gases. So there's no one good way of disposing of addition polymers or plastics, because they just fill up your landfill, they don't rot, they don't biodegrade, they're unreactive, and when they're burnt, they give off nasty toxic gases. Do notice that biopolyesters are biodegradable.
Let's have a look at condensation polymerisation right now, which is probably the most difficult part of the spec. So because it's condensation polymerisation, that means that when these two monomers react, you're going to end up with the loss of a small molecule, which is water. So let's have a look at our first monomer. So hopefully you recognise the alcohol functional group, which is the OH. You've got two carbon chains, so that's why it's ethane. The alcohols appear on both the first and second carbon, which is why its name is 1-ethane 1,2-diol. Over here on the right hand side, hopefully you recognise the carboxylic acid functional group, which is COOH. This is ethane dioic acid, ethane because it's two carbons, dioic because there's two of these carboxylic acid functional groups. So let's try and work out where that water will be lost from. That is the OH from the carboxylic acid, the H from the alcohol end. So that's where the water molecule will be lost, and then it's just a matter of sticking the two ends back together. Right, we're now going to look at condensation polymerisation involving a certain type of polyester called terylene. Now, polyester, as the name suggests, are polymers containing esters. So remember, this is the functional group of the ester. So we need to start by looking at the monomers involved, and these are quite complicated. So our first monomer is a carboxylic acid, which contains a benzene ring with the carboxylic acid functional groups on either end. And we call this benzene due to that presence of the benzene ring, and then 1,4-dicarboxylic acid, and that's telling you that the COOH functional group is present on the first and fourth carbons. Our second monomer is an alcohol, which is ethane 1,2-diol. Make sure you count your bonds and notice that each carbon has 4 bonds, each oxygen forms 2 bonds, and hydrogen forms 1 bond. The name of this alcohol is ethane 1,2-diol. So ethane because it contains 2 carbon atoms, 1,2-diol tells you where the alcohol functional groups come off. Now we're losing water because it's a condensation reaction. So where could we possibly lose water from? Well, it's here. And then you just need to stick the two ends of the monomers together effectively. So it looks like this. Now I'm sticking it onto the alcohol. Keeping this end the same. And this is just one repeating unit really, because obviously it goes on and on and on this way with lots more condensation reactions taking place. But this is actually the structure of pterylene. And notice the ester functional group, which is here. Let's compare the difference between condensation and addition polymerisation, because we've learnt about both in great detail. So let's first of all compare the monomers from which they both start out from. Now with addition, you only have one type of monomer. E.g., if you're making polyethene, the only monomer you'll have coming in is ethene. If you're making polypropene, the only monomer you'll have is propene. And notice with both of these that they are unsaturated, which means they contain a C double bond C, and that unsaturation is essential when you're looking at addition polymerisation. With condensation polymerisation, you'll have two types of monomer, and they won't have a C double bond C. So what sort of bond is made? Well, with addition, you're going to just make a single carbon bond, whereas with condensation, you find that the bond forms between functional groups at each end of the molecule. And then products of reaction, you're going to make just one polymer with addition polymerisation. With condensation, you're going to make two types. Let's look at some uses of plastics now. So use your common sense here, please. Don't spend ages learning this. So where do you find plastics? Well, drinks bottles, plastic bags, general packaging, hose pipes, and insulation for electrical wiring. So you don't find that wires are exposed generally, they tend to be covered in plastic. Now nylon, let's learn the uses of nylon. So you find it in ropes, fishing nets, tents, curtains, and parachutes of all places. Should we try and draw a rubbish parachute? Yeah, it looks more like a jellyfish or a cupcake. Rubbish. Now pterylene, much less well known than plastics or nylon. Just learn that it's used in clothing and to produce thread. And why are we constantly being encouraged to recycle, to use biodegradable plastics? Well, that's mainly due to all the issues involving non-biodegradable plastics. So let's just quickly look at the word biodegradable. It means that it can be broken down using microorganisms. So clearly, a non-biodegradable plastic is not going to be broken down by microorganisms, and it's going to sit in our landfill for hundreds, if not thousands of years. So the issues are, it doesn't break down. The waste pile just gets bigger and bigger. Thus filling up landfill. And you often see on the news that poor birds and animals, they end up getting choked if they accidentally try and eat them. They sometimes get caught up in those wrappers that surround cans of Coke, and you see little rabbits with their heads stuck between the plastic casing. So that's really, really bad. And if they actually manage to eat it, then it sits in their stomach and can't be digested, so it actually leads to their starvation because they can't eat normal foods. If the plastics get into the rivers, then they'll harm the fish. It will also clog up sewers and drains, meaning that flooding may occur, and it's generally really ugly, so it's unsightly. Now we're getting more straightforward and we just need to do a bit of rote learning. So first of all, let's name 2 natural polymers found in food. And remember, a polymer is a long chain made up of repeating subunits. And the most obvious ones to list here are proteins and carbohydrates, which if you take A-level or IB chemistry and biology will become far more of a big deal. So looking at proteins, what are the basic subunits making up the proteins? Well, it's chains of amino acids, which link together by amide linkages. And so if we draw a rough sketch, many amino acids together form the protein. Here's your amino acid. And you can actually break down those proteins, so break apart those amide linkages to produce the original amino acids. And you need enzymes to do this. And these enzymes, which you should know from biology, are proteases. Carbohydrates are slightly different. Obviously, they're not made out of amino acids. They're made out of basic subunits containing simple sugars, which could be glucose, for example. And the way in which these are joined together is through condensation, polymerisation again. So remember that simply means the loss of water, which causes the monomers to join together. Complex carbohydrates again can be broken down by hydrolysis. It involves enzymes. And again, in the digestion topic of biology, you need to know that amylase is a really key enzyme which breaks down starch. A useful reaction we can do with simple sugars is fermentation. And remember, we can use this as an industrial process to create ethanol and carbon dioxide. And in order to cause this reaction to take place, we need an enzyme, which is zymase, which we find is present in yeast. So just to show how this would work, we have yeast containing the zymase enzyme, and that produces ethanol and carbon dioxide as byproducts, which can then be used in bread industry to help the dough rise, and in just making general alcohol for human consumption. In this process, remember, it requires the anaerobic respiration of yeast to produce these useful byproducts. We've already met chromatography earlier. Remember, it tends to be used as a separation technique to look at dyes and inks and food colourings. But we can also use it in this topic to look at the hydrolysis products of both carbohydrates and proteins. The only thing that makes them slightly tricky is that they're both colourless, and remember, dyes and inks contain lots of colour, which is why they're really useful in chromatography. So in order to cope with the fact that they're colourless, we need something called a locating agent.
Thank you so much for watching my video. Well done if you made it to the end. Don't forget you can buy my Science with Hazel Perfect Answer revision guides on my website. They're available right now at www.sciencewithhazel.co.uk.